Afternoon. Students online, can you see the screen? Can you hear me? Supposed to be seeing a plain white screen, the mark on it. All right, good. All right, so we're gonna do some revision today again. We're trying to sharpen up for this exam that's coming up. We're not taking anything for granted. All right. Somebody wants to record. All right. So we're gonna do vectors first. I'm gonna spend maybe about 2 hours on vectors, an hour and a half or so. Take a short break. And we're going to do transformation. Transformation is a kind of bigger topic than vectors. So I don't even know if we can get through as much. But I think I'm going to focus on some of the main things. And we're going to try to do about maybe 6 questions in vectors and about 6 questions in transformation. All right, so that is the plan. So anything you don't understand, you ask. And let us see if we can make this an efficient session. All right? All right, so let me start. Hold on a second. Hold on 1 second. All right, so I'm going to start by doing like a quick recap of some of the basic things in vectors. I'm going to start with a vector equation related to a vector triangle. So I'm going to draw a vector triangle. We're doing vectors now, right? Vectors. So I'm going to draw a vector triangle, a simple vector triangle, like this. And I'm going to say the vector from here to here, and let's label these points, A, B, and C. And it is as if you know the vector from A to B. Let's give that letter X. Let's change this and put the arrow in red as well. And the vector from B to C down here, we're going to give it the letter Y. So these are your vector components, and I'm underlining them to differentiate a vector component from a scalar component. Like, for example, if you want 2y, you would underline the 2. The 2 would be the scalar, and the y is the vector. So the question is now, they might ask for the vector from A to C. So you can look at vectors at this level as, how do I go from A to C, and I must go along vector directions that I know. Like these are like roads. And you have to basically go along those vector directions. So a vector equation that we can set up from this is to say the vector AC, and note now I'm going to put an arrow on top, is equal to the vector AB plus the vector BC. So how do I read this? This equation is not talking about the length of the lines. It is talking about how do I go from A to C, traveling along vector directions that I know. And this is where a lot of people run into problems. They are seeing this equation as a scalar equation. The scalar equation would not include the arrow on top. And it is the arrow on top here that is distinguishing this as a vector equation versus a scalar equation. Because it is absolutely not true that the length of AC is equal to the length of AB plus the length of BC. If you're talking about length, this is not true. So we can cross this equal. It is not true. So this equation, it is correct because it's talking about vectors. So you cannot go reading this equation as if it is a scalar equation. That's the first thing we need to clear in vectors, that a vector equation really is about how you go from point to point, going along vector directions that you know. So how do we read this vector equation? We don't read it the normal way. The equal in a vector equation is sort of different from the equal in a scalar equation. The plus in a vector equation is sort of different from the plus in a scalar equation. They sort of do the same thing, you know, but the meaning of it is a little bit more than just an equal and a plus. All right? So if I'm reading this vector equation, this is saying to go from A to C. That's what this is saying now. To go from A to C. This equal sign, we can read it as is the same as. This means going from A to B first, and that's what does that mean here. We're going from A to B first. This plus in vectors would mean and then we go from B to C. It kind of makes sense. If we want to go from A to C, then we can go from A to B first, and then after we reach B, we go from B to C. And so this vector equation is correct. And that's how you read it. Going from A to B, A to C is the same as going from A to B first, and then going from B to C. So if you know this vector is x and you know this vector is y, then you're good. It means then that the vector AC is going to be equal to the vector AB, which is x, plus the vector BC, which is y. And so AC will be equal to this. So now that you know that AC is this, it is as if you now know this vector across here. Initially, we did not know it, and so we expressed it in terms of these two. But it is as if we now know this. This is now x plus y. That vector across here is now x plus y. So that's how we're starting out. Now, what happens sometimes is that there are questions that will sort of break this line, or break this line into ratios. They break it up into parts. So for example, they might implant a midpoint here and give it the letter M. The midpoint. So basically, M divides this line into two equal halves. And so, since the entire vector AC, we now know it is this. If we want to go from A to M, because M is a halfway point, it becomes that the AM is now half of the AC. And the AC, remember, is this. And so the AM is just half of this. So the AM would then become half of X and half of Y. Right? And that's some of the typical things you'll have to do. But sometimes they don't divide it half and half. Sometimes they divide that line into ratios. Like for example, if I were to divide it, they might tell you something, for example, like the point P on AC is such that AP to PC, for example, they might say it's 1 to 2. Something like that. So it's like P is somewhere on this line, dividing the line such that the AP to PC is 1 to 2. So P divides the line in the ratio 1 to 2. So how do we represent that? What's the significance of that? What I can say is that it's like we have divided the line into 3 parts. One part of it is AP, and there are 2 parts on PC. Mute the mic, please. Mute the mic, please. Somebody's mic is open. Mute the mic, please. All right? So you want to position P on this line so that AP is 1 part of the line and PC is 2 parts of the line. And so it's clear that AP will be the shorter piece and PC is a longer piece. So it's like P now would be positioned here so that it divides the line into 3 parts. And this is where P is. And what happens now, if we were to show the ratio on the line, the AP is 1 part and the PC is 2 parts based on this ratio that they gave us. Now, what is the result of that? What do we glean from all of that? What ends up happening now is that AP is actually 1/3 of the entire AC. And PC is now 2/3 of the entire AC. And so we can write those relationships as well. Vector AP is now 1/3 of the entire AC. You can see it there. It is 1 out of the total 3 parts. So AC now has 3 parts, 1 here and 2 here. And the AP is 1 part of it, 1 out of 3. And so AP is now 1/3 of AC. These are some of the things you have to do in vectors. Remember again, you know, that the AC is just x plus y. And so this AP would now be a third x plus a third y. Because the AC, remember, is x plus y. I know taking a third of each part. All right? And if you were to write an expression for PC from the diagram, the vector from P to C will be 2/3 of the entire thing. So we can write another equation here that says PC is now 2/3 of the entire AC. Again, the AC is just x plus y. So this would work out to be 2/3 of the x and 2/3 of the y. And this would be a PC. And then sometimes you have to do some other stuff. So we're just dealing with now the ratio that they will introduce sometimes on these vector diagrams. All right. I want us to talk about the negative in vectors quick. All right. The negative in vectors. I'm going to copy this diagram down. I'm going to introduce the negative quick and fast. So I want to get through this introductory part first, and then we're going to do some questions. All right. So if you have this vector, AB, let me take these off. Since this is the vector from A to B is x, then the vector from B to A is actually negative x, because you're coming in the opposite direction to the x to go from B to A. Similarly over here, since the vector from B to C is y, then if you're going in the opposite direction, then we can say the vector C to B becomes negative y. So the negative in vectors really means you're reversing your direction. Once you're going in the opposite direction to a vector, you're reversing the direction. Mute the mic, please, everybody. Mute the mic, please. Mute the mic, please. Mute the mic, please. All right. So that's what the negative means in vector. We're going to see the use of it in some questions. All right. So I want to also now introduce a popular concept, which is the vector parallelogram. All right. Just some of the common things that you see in questions. The vector parallelogram. So might be a parallelogram like this. And they like to give you a vector parallelogram. So it's a parallelogram. And you might label it up again. This might be the point O, A, B, C, for example. That's a parallelogram. It means that these two sides are equal and parallel. And these two sides are equal and parallel. So if this vector down here is the vector V, for example, from O to C is V, then automatically the vector up here is also V. Because equal vectors, once vectors are equal, they have the same length and they are parallel, no matter where they are located. So even if I draw another vector down here, horizontally like this, and it is the same length as that, and the same direction, then this vector down here is also V. Right? Because the vector really is about about direction and magnitude and direction. All right? And then similarly, if this vector here is the vector U going up this way, then this vector from C to B is also U. That vector is also U. So once you know this one, you automatically know that one across here. Vector parallelogram. And then a common question I might ask you is, for example, what is the vector BC? No, AC in this diagram. What is the vector AC? I can see it on the diagram. To go from A to C on this diagram, going from A to C, and you always want to basically start out in the same direction as the vector that you're connected to. So because I'm connected to this vector and I want to go to C, I want to go in the same direction Generally speaking, you don't want to be going against the flow of the vectors. You want to be going in the same direction as the flow of the vectors. So to go from A to C, based on this diagram, I could go from A to B first. Let's write it. And then I can go from B down to C. B to C. And so the vector would work out that because the AB is V, so this will be V. But then it's a negative U. And if you think of not the letters, the A, the B, and the C, but think of the vectors, then you can literally see this, that to go from A to C, you go from V, and then you go the opposite direction. So you go V this way, and then you go the opposite direction to the U. You're going down, so you're going a minus U. That is the vector. So once we now have this vector, AC, it is as if we now know this road across here from A to C, because we now know this vector. And so now we can traverse along this vector here, because we can use this to traverse along that vector. So then, for example, if we have a point on this vector across here now, from A to C, let's say we know of this point, the midpoint. We're going to call that M. This point M. And let's say from this now, we want to get the vector from M to B. Because we now know this road, because we now know of that vector, we now know it, we can now go from M to B, traveling along this purple vector, because we now know it. We have it now. And if M is the midpoint, then M to C is going to be half of this vector, because M is the midpoint. So we can set up, for example, another vector, which will take us from M to B. To go from M to B, we now can go from M to C, and then go from C to B. So go M to C, and then go from C up to B. And that will take us from M to B. The MC is just half of the AB. The MC in on this diagram is half of this vector AB. So this MC is half of this. So this would then be half of the V minus half of the U. That's what this is, you know. Half of this vector. And you're adding back this CB. And the CB would just be this vector U going in the same direction as the U. So you would add that U. And when you're doing vectors, you always want to consolidate your vector components. What I mean by the vector components in this case would be the U and the V. So I want to write this expression, I want to write this now in terms of one U. So I'm going to work out these two U values together. This is the only V term there. So this will simplify to half V, and then a whole V minus a half U gives me a half U. And that will be a vector from M to B. It's a simple example. All right, and those are some of the things we can do on a vector parallelogram. Remember, initially, we would not have known this. But once you write it in terms of the V and the U, then it's almost as if now you know that vector across here, this vector AC. So once you have this vector AC, it is now as if you know this path across here. So you can go to portions of it or the whole of it. You can go parts of it or the whole of it. All right? That's a vector parallelogram. Now, vectors are not only expressed with these notation, these symbolic way. They can also be expressed in coordinates, like on a graph. All right? So we can introduce now what we call the position vector. So if, for example, you have a graph, and this is the point O, I have a point P up here, and the coordinates of this point P is 3, 4. Using coordinate geometry to go from O to P, you would have basically gone 3 units across here. And let's write it that way. Let's write it 4, 3. This is how the diagram looks. So this will be 4 across here, 4 this way, and they would have gone 3 up to 3. And if they want the vector OP, which is now the position vector of P, the vector OP, it is basically the vector that takes us from O straight to P. It's basically this vector. That's the vector OP. And the vector OP will have the same values as the coordinates, because we are saying it is as if we have displaced from O to P 4 units to the right and 3 units upwards. So we have gone 3 units upwards. So you write that as a column vector, 4, 3, carrying the same coordinates as the coordinates. So the position vector of a point and the coordinates of a point will have the same values. And the position vector is the displacement from the origin to the point. And so a lot of times vectors can be written and be presented like that. We have to do calculations with vectors like these as well. Now, having gotten these position vectors, you can get questions where you also have to find what we call displacement vectors. So these are position vectors. You can also now have displacement vectors. So displacement vectors now is like the vector that takes you between 2 points in that space. All right. So if we were to, let's copy the diagram down and introduce another point on it, just for illustration purposes. I'm just trying to cover some of the basic things first, and then we're going to run and do some questions. And so let's say now, let me take these out. That's the vector OP. Let's say now there's another point out here. And this point is R, or this point is Q. And let's say that point Q has coordinates. Well, basically the X value is larger, so give it 6 or give it 7. And the Y value, let's give it 1. This point Q. So Q is now the point 7, 1. So this is the vector OP, remember? And so the vector OQ now will be the one from the origin O to Q, that the position vector of Q, like this. That straight vector out here would be the position vector of Q, OQ, with the arrow on top. And OQ would be written similar to the OP, having the same values as the coordinates, 7, 1. That's a position vector. So we have 2 position vectors now. We have OP and we have OQ. So OP is 4, 3 and OQ is 7, 1. So what would that mean in a case like this, for example, is that we might be asked to find the displacement vector that is taking us from P to Q, for example, this red vector, from P to Q. That's called a displacement vector. And that displacement vector PQ can be expressed in terms of these 2 position vectors. And it is as if, again, we know these 2 vectors. We know these 2 vectors. We know the OP and we know the OQ, and we don't know the PQ. So what we can say is that to go from P to Q, you could come back to O first from the P, and then go from O out to Q. So like we're starting at the P, and we're coming back to O first, and then from the O, we're going to go out to the Q. And that sets up for us a nice little formula for displacement vectors, because we can write it like this now. We can write it like this. To go from P to Q, we could go from P to O first, and then go from O to Q. But if you notice, this PQ is really PO, sorry, this PO is really OP switched around. So the direction that is opposite. What we can do is switch around the letter, switch around the direction, and introduce the negative. And so this is the same as minus OP, because the minus means a reversal of direction. And they are adding back the OQ. And if we write this in a more aesthetic way, then we would end up getting OQ minus OP. So PQ then would be OQ minus OP. And this is the formula I want us to remember now for the displacement vector. I refer to it as O times the last. This would be O times the last. O times the last. What do I mean by the last? Q is the last. O times the last. Q is the last. Minus, and this one will be O times the first. So a displacement vector is O times the last minus O times the first. So in simple terms, simple examples, if I want the vector Mn, and I know both position vectors, I know the position vector of M, and I also know the position vector of N, then this can be written as On minus Om. O times the last minus O times the first. If it is, for example, Rs, and you want to find the vector Rs, and you know both of them, you know the OS and the OR, then this simply would be OS minus OR. O times the last minus O times the first. And then once you know these position vectors, you calculate them. So if we're working on this one up here, the P and the Q, let's go back here and do it and finish it up. Then this PQ that we wanted, it is OQ. Now remember now, OQ is this vector, 7, 1. Minus OP, and the OP is this vector, 4, 3. And if you do this calculation, it's really simple, it's a matrices subtraction now. It's 7 minus 4, which is 3. And this is 1 minus 3, which is negative 2. And so we have a conclusion. This is basically saying, to go from P to Q, we're using this vector. And this vector is like a translation vector in transformation. It means to go from P to Q, this 3 means that we're going to go 3 units to the right. And this negative 2 is a vertical movement. We're going to go 2 units downwards. So it's like P is here and Q is here. To go from P to Q, this vector is saying go 3 to the right and 2 down. Why is it down? Because of the negative. And you can literally see it on the diagram. See it here? Let me shift this up. To go from this point P to this point Q, it is saying we go 3 to the right, 3 units to the right, and then go 2 units downwards. So it's 3 to the right, and then 2 units downwards, a negative 2, to go from P to Q. So this basically is telling us that what we get by calculation must match what the diagram gives us. What you get by calculation in vectors must match what the diagram gives us. All right? So you must always have that consistency between the calculation and what is shown on the diagram. All right, so that's displacement vector. All right, let's talk about now parallelism and collinearity. All right, and we're going to finish up this little introduction. I'm going to put it all together in some questions. All right, a lot of the times, all of this is all about questions. But let's talk about parallel vectors now. Now, oftentimes CXC will ask you to show that two vectors are parallel. Let's start that way. When two vectors are parallel, one can be expressed as a multiple of the next. So for example, if I end up having, for example, PQ equals 3RS as an equation, this means that the PQ and the RS are parallel. It's just a size difference between them. It means that the PQ is longer than the RS by 3 because you have to multiply the RS vector by 3 to get the PQ vector. So it's like the PQ vector will be here and the RS vector is a third of it. This will be the RS. RS is a small one. So you have to multiply this one by 3. 1, 2, and a third one, 3 of them, to get one PQ. But they are parallel. Once you can express one as a multiple of the next, it means that the vectors are parallel. So the question is, sometime when CXC asks you that, to do that, to show that two vectors are parallel, what are some of the steps to do that? And I give my students 3 steps. A 3-steps process. I'm going to do it with an example. To show that two vectors are parallel, 3 steps. The first step, or step 1, is to get rid of any fractions. Why are we getting rid of fractions? Because it is more difficult to see the relationship between numbers when they are expressed in fractions. So for example, it's easy to see the relationship between 3 and 9. That's a 3 times relationship, or the relationship between the numbers 3 and 12. It is obvious that this one is 4 times this one. Obvious. But if I write the number a third and then I write 7/5, it's more difficult to see the relationship between these two numbers. So if a vector is expressed in terms of a third and another vector is expressed in terms of 7/5, and there's some parallelism between them, it's going to be difficult to see by how much they are related. So that's why you don't want to get rid of the fractions and express the vectors in whole numbers. All right? You want to express them as whole numbers. That's the first step. Get rid of the fractions. Step 2 is you want to make the two vectors become equal. So we always say multiply the small one up to make it equal the large one. All right? So you multiply the small one up, multiply up the smaller one to be equal to the larger one, the larger vector. And when you do that and they are now equal, you go to step 3, which is the final step, which is now to equate the vectors. To equate the vectors. Those 3 steps will allow you to show that two vectors are parallel. Now, there are times when it is obvious what the relationship between the vectors are, and you don't have to do all of this. A lot of the times it is obvious the relationship between two vectors. So for example, if I give you two vectors like this, RS is the vector 2, 3, and PQ is the vector 4, 6. Then it is obvious that this one is 2 times that one. This big one is 2 times this small one, obviously. So we are able to write that PQ, the big one, is equal to 2 times the small one, which is RS. So if we get numbers like those, that's a problem. And then this now would mean that they are parallel. And that's what you would have to show to mean that they are parallel. But sometimes it's not as straightforward as that. I'm going to give you an example. All right? So an example of this, I have one on my paper here, is that we are given two vectors Mn, and one of them is half u, vector u plus 3/4 v. And that vector is parallel to another vector rs, where this vector rs is 2/3 u plus v. Those two vectors are parallel now. And CXC wanted to show that they are parallel. To show that they are parallel, you need to get an equation like, for example, Mn equals some number k, some factor k, some multiple k of Rs. So the question is, what is that? All right, I'm going to go through the 3 steps with this example now. So the first step, as I said, is to get rid of any fractions. You don't want no fractions. You're going to multiply these vector equations so that no fractions remain. And you want to get all the whole numbers to be looking at. So if you look at this one, if you multiply through by the lowest common multiple of the denominator, which is a 4, that will get rid of all fractions. It will cancel out this half, and it will cancel out this quarter, and give us whole numbers. So I'm going to multiply this first one by 4 to get rid of fractions. Multiply it by 4. When I multiply by 4, you have to remember to multiply each term by that 4. So multiply this 4mn first by the 4. I will get 4mn equals, then multiply this by 4, it's going to become 2u, because half of 4 is 2, or 4 times a half is 2. Then multiply this one by the 4, it cancels the 4 here and leaves us with 3v. And we have got rid of the fraction. So we have written this one as that without the fractions. Then now, to get the fractions out of Rs, we need to multiply through by this 3. So if we take the Rs and we multiply through by 3, it will eliminate the fraction from this. We have to remember to multiply each term by 3. So multiply this Rs by the 3 first. You get 3 Rs that we're talking now. Then you multiply this by the 3. The 3 is cancelled and we get 2u. And you multiply this v now by the 3, we get the 3v. And what you notice already is that they are already equal. So there's no need to do anything else. There's no need for step 2, which is to multiply the small one to make it equal the large one. You don't need step 2 in this example. Sometimes you don't need step 1. Sometimes you don't need step 2. Sometimes you can just jump straight to step 3. It's just based on what you're given. But the aim is to bring them to a state where you can equate them. Right? So if you look at these two now, we have the two vectors expressed in terms that are equal to each other. So because those vectors are equal, it means that we can now equate. We can jump to equate, the last step. So because this thing equals that, 2v plus 3u, and this thing equals the same, 2u plus 3v, 2u plus 3v, both of them is 2u plus 3v. It means that this and this equal. That's what it means. It therefore means when we equate, it means that the 4mn is equal to the 3rs. And this now means that the vectors are parallel because they have expressed one as a multiple of the next. If you like, you can divide the 4 under here and say mn is 3/4 of Rs. But it don't matter. You can leave this one. It means that they are parallel. So this, by doing this, by expressing one as a multiple of the next, we are able to say that the vectors mn, vector mn is parallel to the vector Rs. All right? So those of you who want a process to show that vectors are parallel, this is it right here. This is a 3-steps process that will work for you every time. As I said, sometimes it is pretty obvious what the multiple is, but especially when they give you the vectors with fractions, that's what you want to do. Get rid of the fractions. You multiply the small one up to make it equal the large one. And when two vectors are equal, they equate. And you must end up with an expression looking like this or something like that. That would now mean that the vectors are parallel. Another thing they ask you to do in vectors is to show that 3 points are collinear points. So, like on the vector diagram that I had earlier up here, let me show you the one with the parallelogram. They like to do it in the parallelogram question. What I might do sometimes is give us a situation like this, where they give you a point here. Let's say that that point is P on the midpoint of this one. Then they give you a point maybe 1/3 this way on this line. So I point to another point here, that point might be 1/3. And then you have to show that these 3 points, let's say that this point here now is T, for example. And then you have to now show that these 3 points are collinear. P, T, and B are on a straight line. P, T, and B. It's a common question to show that 3 points are collinear. Sometimes you have to do it with just vector equations, vector values, vector numbers. So it's 2 things you have to do to show that 3 points are collinear. The first one is to show that you have parallel vectors. So the same steps that we use to show parallel vectors here is the same steps we use to show when points are collinear. So you still have to do these 3 things to show collinear points. Because to show collinear points, you have to show that you have parallel vectors. But in addition to having parallel vectors, you must have a common point on those 2 parallel vectors. That is when 3 points are collinear. I'm going to give an example again. All right? So collinear points, 2 things you have to show. You have to show that you have parallel vectors with a common point. All right? So let's write an example for collinear points. And then we're going to do some questions after this. So it's going back through some of the basics, and then we're going to do some questions. All right? So to prove collinear points, collinear points, as I just showed, is when you have 3 points on a straight line. All right? 2 things you have to show. You have to show that you have parallel vectors to show what you have to show. You have to show that you have parallel vectors between the 3 points. That's the first thing you have to show. And the second thing you have to show is that there's a common point. Parallel vectors with a common point. When these 2 things happen, it means that the 3 points involved are collinear. The 3 points involved are collinear. So for example, if you have 3 points, say you have P, Q, and R, and the question I want to show that those 3 points are collinear. You need to end up with an equation like this. For example, you need to end up with an equation like, for example, vector PQ is equal to 3 times the vector QR. For example, you want to get something like this, for example. Because by getting one other multiple of the next, it would mean that you satisfy the first condition. They are parallel. PQ is parallel, that's my symbol for parallel, to QR. That's the first thing. And then these 2 vectors, it is clear now for this example, this is just an example, that your Q would be a common point. The Q's are the 2 vectors that are parallel. So the second thing here is that the Q is a common point. And once you have these 2 things happening, then you're able to draw the conclusion and say, therefore, the points P, Q, and R, they are collinear. They're on a straight line. Sometimes I spell collinear with 2 L's, depending on whether it's American spelling or the British spelling. So this is what you want to do. So let me do an example now. So remember, these are the 2 things you have to show to prove collinearity. All right? show that you have parallel vectors with a common point. So let me write an example now. All right, so remember the same steps that you use to show that two vectors are parallel, the same steps to show that you have collinear points. Because you have to first show that you have parallel vectors, and then one of the points is going to be common. All right, so I'm using these examples. I'm using the vector PQ, and in this example, it is 3 over 2A, vector A, minus a quarter B. And my second vector is QR. And in this example, my QR is 2A minus a third B. And I need to show that I need to show that the 3 points involved, PQ and R, are collinear. PQ and R are collinear. So the thing is, you must use two vectors between the 2 points. Any two vectors between the 3 points. Any two vectors between the 3 points can be used. We always want to use two vectors that you can find easily. So the first step is to show that these two vectors are parallel. So the same steps that we did before. First thing is to get rid of fractions. So we don't want the fractions. The fractions make it difficult to see the relationship between the vectors. So to get rid of the fractions out of this one again, we're going to multiply 2 by 4 again. Lowest common multiply the denominator. It's 4. So multiply this one by 4. That will eliminate all fractions for us. Multiply this one by 4. Remember, when you multiply by 4, you're multiplying each term by the 4. So multiply this by the 4, it becomes 4PQ equals, multiply this by the 4, you're going to get 4 into the 2 goes 2 times, or 2 into the 4 goes 2 times, 2, 3, 6. So we're going to get 6A. We multiply this by the 4, it eliminates the quarter. So I'm just going to get minus B. So when I multiply this vector by 4, it becomes that. I also need to get the fractions out of this one. Fractions make it difficult to see the relationship between the vectors. We want to express the vectors with whole numbers so we can see the relationship easier. We don't want to be guessing and looking too hard. So let's get rid of the fractions. So to get rid of fractions out of this one, the lowest common multiple in the denominator is just a 3. So we're going to multiply this one by 3. And that will get rid of all fractions from that equation for us. When we multiply this by the 3, it becomes 3QR equals, multiply this by 3, it becomes 6A. Multiply this by 3, it cancels the third and leaves me with a negative B. And see, both vectors are now equal. So we can be able to equate because this now and this, they're the same. So if those two are the same, it means that these two are equal. So we don't have to make any other adjustment. We can now equate. All right? So we can now equate. So because we have them equal to the same vector, we can now equate. I needed to remember these steps, guys. I don't think you're going to see them in the textbook. So it means that this thing equals this thing. So we can now write that 4PQ is equal to 3QR. Now because we have this equals this, one vector is a multiple of the next one. Because remember now, we can divide by this 4 and put it instead as 3/4 here now. 3 over 4. Right. 1 is a multiple of the next. We can do that but we can leave it like this as well still and leave the 4 out here. This still means that they are parallel. And you have to write out the conditions for the examiner to see. The first condition for collinearity is that they are parallel. And by getting one vector equals a multiple of the next one, it means that they are parallel. So we can write that PQ is parallel, it's my symbol for parallel to QR. That's the first thing must happen for collinearity. You can put the vector on it if you want, or you can leave it off. Neither here nor there. The vectors are parallel, so the lines are parallel. Without the vector arrow on top, it is just the lines that we're talking about. With the arrow on top, we're talking about the vectors or the directions. That's the first condition. The second thing that you must state is a common point. And the common point is clearly the Q in this example. Q is a common point. So you state that as well. Q is a common point on those vectors. And so now, because you have these two conditions satisfied, we can draw the conclusion and says, therefore, the points involved, P, Q, and R. P, Q, and R, they are collinear, meaning they are on a straight line. And that is it. One last thing I want to mention before we move on to the questions is modulus. Modulus is just the length of a vector, how long the vector is, size. Simple. And it basically comes from Pythagoras' theorem. Simple, it's not complicated. So for example, if I have a vector like this, I'm going to talk about now the modulus, which is same as the magnitude, which is same as the length of the vector, which is same as size. All of those things is the modulus. So if I have a vector, so let's have a vector v, like this. Just making up one, right? That's a vector v. Underline it. And v is such that to go from this end, from the tail to the nose, I have to go, let's say I have to go this number of units to the right. Let's say this is 5 units. Let's say this is 4. Let's use simple number. Let's say this is 4 to the right again. And then I have to go 3 up. 3 up. It will mean that this vector v is equal to 4, 3. That vector v is equal to 4, 3. Now the modulus is basically how long is this line? That's what the modulus is, you know. How long is that vector line? How long is it? What's the size of it? If you use Pythagoras system, remember this is a right angle triangle now, you know. Right here is 90 degrees, you know. Because this will be in the x direction, this will be in the y direction. The angle between the x direction and the y direction is 90 degrees. So you have a right angle triangle where, you know, two sides. And this side now is like your hypotenuse, like you're trying to find the length of the hypotenuse. That's what the modulus is. And the modulus is written by just putting these two lines on either side. That's a symbol for it. The modulus of v is written like this. And it's Pythagoras' theorem you're using. So it becomes the square root of this folly squared plus this folly squared, which really is this side squared plus this side squared. 4 squared plus 3 squared. So the modulus really comes from Pythagoras' theorem. It is not complicated. And this will basically work out to be 5. If you work it out, it's going to be 5. And we say units because modulus is a length. So the modulus of v, the length of vector v, is 5 units. That's what modulus is. Now, even if one of the components was negative, let's say the vector was in this direction instead. Let's say the vector was, for example, here, this way. Vector v was this way. So you're going to use the same value for simplicity. Okay, maybe use 3 this time, 3 to the left, and 4 up. So go 3 this way. That will be negative 3. And then 4 up. If that is the case, then this vector v, if you write it in the column format, it will be negative 3, 4. But the negative is always the first value in the vector in this column format is always a horizontal movement first, or the horizontal displacement. And the second value is always a vertical displacement. So because this value is negative, it means that you're going to the left. You're going in the negative x direction. And because this value is positive, it means that you're going in a positive y direction. You're going up that way. So basically, that is your vector. The length of this still, if you treat this as the length of it is 3, the negative is just direction. I treat this as if the length is 4. Then the modulus of this vector would still be the square root of this value squared, which is really this side squared. You don't need to put the negative on it. Because even if you put the negative 3 on it and square it, it's the same as the 3 squared. But you don't need to put the negative on it. So when you find the modulus, you don't need to put the negative. So it will just be 3 squared still, plus 4 squared this time, which again, this one would work out to 5 units. I deliberately use these values for that Pythagorean 3, 4, 5 triple. All right? All right, good. Everybody good so far? We're going to jump to some questions now. All right, so I try to just do a little recap right there. I'm going to do some questions now. I'm trying to do some of the recent questions, all right? So let's go. I looked at some of them before, and I'm going to let us do January 2021. January 2021. Let's start with that one, because I looked at a couple of them before. January 2021, where are you? Right here. All right. So the vectors question is always at the back. Last question. The vectors and matrices section. Sometimes I put transformation around there as well. All right. Oftentimes it's the very last question, as you can see here. All right. So let's look at part B. Part B is a matrices. Actually, that's a transformation. So we're looking at this question to begin with. A nice question to start as an example. All right. This is revision for students of this program. All right. So it's always good. More maths equals better maths. All right. So this question says, the diagram below shows triangle OPQ. It says the vector OP is 3u. That's right here. See there, 2u and u makes 3u. All of this is 3u going up. All right. And the vector OQ is v. See it right here, so from O to Q is this vector v. So it is as if we know this road and we know this road already. So to begin with, you want to start with those roads that you know. The vectors are like roads to get around the diagram from point to point. Think of it that way sometimes. It's a Q is the midpoint of OR. So this point Q is the midpoint of this entire thing. So it therefore means that this side and this side, they are the same length. Right? Let's divide another way. Since this is the midpoint of this whole line, it means that this length and this length is the same. But then it is a one straight line. One straight line. And so they have the same vector direction. So since they have the same vector direction as V, but they are the same length, it means then that the vector from Q to R is also equal to V. Once the lines are parallel and equal in length, they are the same vector. So it means that the vector from Q to R is also V. I'm going to put it on there. This is also V, like this one. But I go to that so far? Yes, sir. Online? Good. Then it said, M is the midpoint of PQ, and that is shown here. But it's as if we don't know this vector yet. We don't know this road yet. Because there's no vector shown on it. But we're going to work it out, you know, and after we work it out, then we will know it. All right? We're going to work it out and then we will know it. And they tell us that L is on OP such that OL is 2/3 of OP. Let's look at it. And actually divide it up for us already. L is right here on OP such that the OL, sorry, right here, is 2/3 of the entire line. 2/3 of the entire line. So OL is 2/3 of the entire line. But they have already divided it up first because the entire vector, remember, is 3U. And if OL is 2/3 of the entire thing, then it is 2/3 of the 3U. 2/3 of 3U is going to be 2U because the 3's will cancel. And they have done it for us already by putting the 2U on it. And so the other part up here is just U. So they have divided up the vector first. In the past, you will have to figure that out yourself, but they're helping you. In recent times, they make the questions easier by helping you with those things. So they have already divided up the 3U for us into 2U plus U. First question wants us to calculate the vector LM from L to M. All right. So the question is now, how do we go from L to M? Now notice, to go from L to M, you have options. We want to do it the shortest way possible, the easiest way possible. To go from L to M, I would say, go up here to P first, the use the red ink. Go from L to P first, up here, using the U, and then go from P to M. That will give us LM. The problem is that we don't work out the vector on that road yet, on the PQ yet. We know that the PM is half of the PQ, See there, the PM, because this is the midpoint, it is really half of PQ. Question is, can we find PQ? Yes, because we know the position vector of the P, and we know the position vector of the Q. We can also look at the diagram and see that we can find PQ. Go from P to Q. We can come back along this side in the opposite direction to the 3U, so that's a minus 3U. Then we can go from the O out to the Q this way using the V. So it will be minus 3U plus V. That's what the diagram is showing us. So you have multiple ways to do it. But since we don't know the PQ yet, and we're going to need it, just I think that this question didn't ask us for the PQ. Most times the question would have asked for the PQ first. But we need it. So I want to calculate the PQ over here to help ourselves. So the PQ is equal to, now listen, when I am doing vectors, and I know the position vectors, then I use the formula, O times the last minus O times the first. If I don't know the position vectors, then I use a diagram to see how I go from point to point. So this time, I'm just going to use OQ minus OP. That's O times the last minus O times the first. Why am I doing it this way? Because I know them. I know the position vector of the Q is right here, and I know the position vector of the P is right here. But what we get by calculation must be consistent with what is on the diagram. So this works out, the OQ is V, minus, the OP is 3U. So that's what the PQ is, the vector PQ. Down here. So like we now know that vector, we have it. Because we have this vector now, we can travel on it. We can travel along this vector now because we now know it. We know the vector. We have it. We didn't have it before. We worked it out. We realized that what they're asking us for requires us to travel along this vector here. The vector is like a road. We need it. So we work it out first with what we have. And the PM to here is just going to be half of this. Sometimes when you calculate a vector, guys, you can sort of double check to see if what you get makes sense, if your calculation makes sense. Let's look at it. This PQ is saying, go in the direction of V and then go minus 3u. Let's look at it. Go from P to Q. This answer is saying go a V and then minus 3u. Let's do it on the diagram and show it. Let's do it on the diagram. I'll move this out of the way and show you. Starting at P, I can go a V. Remember, any line that is parallel and equal to this is a V now. So I'm going to come here. This is a V. But this line is a V. Let me show you. So this is a V. From here to here is a V. I can transfer this V to up here. That is a V still. So this is a V now, this is a V. Then I want minus 3u. All of this is a 3u, But minus, this is a 3u going up this way. Minus 3u would be the opposite direction, down. Put the arrow down. All of this is 3u, but the opposite direction. So this is a minus 3u. So I can take this minus 3u that I have over here and put it over this end. You see? It takes us to Q. So it is consistent. See? Go a V and then go minus 3u takes us from P to Q. So that shows me that my answer is correct. It is consistent. But understand that? Online, everybody good at that?
Yes, sure.
All right, good. So this is the vector though. We now know this rule, so we can go along it. So based on that, then we can now calculate the LM, sorry. Now look at the diagram, as I said, to go from L to M, we're gonna come up to P first. Let's write it out. We're gonna go from L to P, and then we're gonna go from P to M right here. P to M. That's what the diagram tells me. Shows me how to go from L to M. But L to P, going along that the vector direction, which is a U, and then go P to M. We have to recognize that the PM is just half of the PQ. So I can replace this PM and put half of PQ instead. So this then becomes LP, and then this PM really is just half of PQ. Now, why would I express it in terms of half of PQ? Because it is PQ that I know. It is PQ that I know. So now I need to do half of the PQ that I know. So then I can put in the values now. The LP clearly is just this U right here. Remember, I have to give the answer in terms of the U and the V, guys. You can't leave the answer like this, See, the question says, write in terms of the U and the V. That's the U and the V on the diagram. So you cannot leave it like this. You have to give the answer in terms of U and V. So right, so the LP is U right there. So I want to put U for the LP. So what they normally do is write these vector components bold letters, but I always underline them. Then we need half of PQ. Let's bring back the PQ in on the screen where we can see it. Then we worked it out here a while ago. We now need half of it. We need half of this thing right here, half of that. So half of that is simply half of this part and half of this part. So it's simply gonna become half of the V, that's half of this part, and when you half this, it becomes minus 3 over 2U. Everybody understand that so far? This right here is half of PQ. Everybody understand that before we move on?
Yep.
Yes, sir. Yes, sir.
All right, good. And then you must always consolidate your values. Don't leave it like that. So this U term and this U term, put them together. This is the only V term in it. I'm going to write that back first. So put that as half V, and I'm going to put in this U and this U. Now, you see this U, I can think of it as 2 over 2. Why am I doing that? Because this must have the same denominator as that. So I think of it as 2 over 2. And so because them have the same denominator, it's like I'm doing now 2U minus 3U. 2U minus 3U is a minus 1U. and it's all over 2. So I'm going to get minus 1 over 2u. That's my answer. But I understand that?
Yes, sir.
Online. And then I like to check if this answer makes sense. Check if this answer makes sense. If this answer would take it from L to M. Sometimes you just do that little quick check. Because, let me show you now. I'm going to do that little quick check. So this is saying I must go half in the direction of V and then minus a half U. All right? So watch this now. A half V is about this, you know. That's what a half V is, right? That's about a half V. I'm gonna move it up here and show you now. So this is about a half V. Move it up to the L. And then I want a minus half of U. See? Minus half of U. Minus half of U. So see, you know, this is a whole U, and I don't want a whole U. I don't want half of it. Half of it is about this. I will put the minus, or put in the arrow down. This is a V already, you know. That's a half V. And I'll put the arrow pointing down on this half of U now. I'm going to shift this over now. I'm going to shift this over and put it here. See? Basically taking us to the M. To the M. Maybe I didn't draw this long enough. But this should come here to get a half. Let me draw it over. I want half of this line. That's a whole U. I want half of it. Half of it is maybe up to here. Half of that line. Or going in the opposite direction. So going this way. That's a half a U, and it is minus, going the opposite direction. So the calculation is telling me that I must do that. Just about correct. So I can accept it. But this looks like this is a half U, half V. This is a half V. And this is a minus half U. This is a minus half U. So I can accept the answer like that. Now let me show you now how you wouldn't accept it. Suppose I made a mistake, right? And instead of a minus here, instead of a minus right here, I made a mistake and I ended up and put a plus. I'm going to check it. So I have a plus half U instead. If I made a mistake and I put a plus. Then when I come and check on my diagram, right? The plus half U, this will be a plus half U going this way. So I put that plus half U this way. It will be taking me away from the M. So I would know that I made a mistake. You get me? So that's the kind of check you can make sometimes with these guys. I'm taking my time on this one, you know. But the answer is minus. So let's go back and do the right thing. It is minus. But that is the answer right there. So far. All right? That's the answer for the first part. The next part now says, we must calculate the vector PR. Let's look at the diagram. Over from P to R. We can decide if we can get the position vector. It's kind of easy to go from P to R. It's kind of easy. Why is it easy? Because we know OP. OP is 3U. And technically we know OR as well, you know, because OR is 2V out here. We can write it. Because it's V plus V. So OR is 2V. So if we were to write them out, the OP is 3U and the OR is 2V. So we can calculate this PR right here. The PR that we want becomes O times the last, OR, minus O times the first, OP. OR minus OP. When I know the position vectors, I tend to use this formula to do it, rather than use the diagram. All right? And so this then is just going to be 2V minus 3U. To go from P to R, I got 2V minus 3U. I can check it on the diagram again if you want. Look. I can check it on the diagram, move this out the way again and show you. This is saying got 2V minus 3U to go from P to R. See 2V here, that's 2V, same length as this. I put it up there, so 2V. and then minus 3u. This is 3u this way now. This way. So minus 3u is 3u down this way. So see there, this will be minus 3u. So this is 2v, and this is minus 3u down here. So it's minus 3u. So it is correct to go from P to R. I can go 2v and minus 3u. So I can accept those answers. So you can always do that like a quick check as you go. Don't just be working blind. Do that, those little quick checks as you go. Right? So this answer is correct. I'm going to leave it. Let's put it down here. Let's put it down here. This is the answer. This right here. Let's shift it around a little bit. Because I think I'm going to need it. This is the answer right here. This. 2v minus 3u. And the last part now says, show that the points L, M, and R are collinear. But I want to pay attention to this now. So if you don't know to do this, pay attention. You only need to see it done once. The same way all the time. Now the first thing, you have to use vectors with these 3 points. You cannot use a vector that is not one of these 3 points. So for example, you cannot use a vector, since we want L, M, and R, right? L, M, and R. We can't use P. We can't use any vector with a point P on it. You have to use 2 vectors with these 3 points on it. So that you're going to use LM, LR, MR. Any 2 of those 3 will work. And a lot of the times what you do, you look to see if you have any as yet. You need 2 vectors with these 3 points. So you can't use this one because this one has P in it. Right? You can't use that one. That one has P in it. You need 2 vectors between these 3 points. I'm taking my time on this one. So you're going to look and see if you have found any vector yet with these 3 points. Sometimes you would have found 2 already. Sometimes you would have found 1 already and you need to find another one. So let's go and look what we have already. Can't use PR. Because PR is not one of the points that we want to show that is collinear. So we cannot use this vector. That won't help us. Let's look what else we found already. We found LM. See here, LM. Let's look at it. We found LM. So this is the vector that we can use. LM. So I'm going to copy that down as one of the vectors that I'm going to use. I'm searching for 2 vectors that I'm going to use. I have to find 2 vectors that I'm going to use, show that they are parallel, and that is a common point. So this is one of the vectors I'm going to use, LM. Let me copy it down here. So I'm writing down the vectors that I'm going to use to prove the collinearity. Put down the vectors. I have to show that they are parallel. So that's one of the vectors that I'm going to use. So I already have LM. So I need another vector now with R in it. So it is either LR or MR. Come, I already have a vector with the LM. So I need another vector with the R on it. It's either the LR or the MR. So I'm going to look at the diagram now and I'm going to see which of these 2 vectors is easier to find. Which of them is easier to find, the LR or the MR? We want to do the mathematics the easy way. LR or MR, which one is easier to find? Let's look at the diagram now. Because we don't have it now, so we have to calculate it. We're going to work out it. So looking for LR or MR. Because we already have LM. We have this one already. We have this one already. So it's either LR or MR we're going to use now to prove collinearity. So look at the diagram now. See the points that are collinear here now. See them here now. L, M, and R. See them here? You're on a straight line. If you draw a straight line, you're going to get them on a straight line. See them there? That's what we're trying to prove. But you don't prove by drawing on the diagram. So tell me now, guys. LR or MR, which one is easier to find? Look at the diagram. Which one is easier to find? Somebody online tell me. Which vector is easier to find? LR or MR? Which one is easier to find based on this diagram? LR or MR? Which one is easier to find? We're going to do the mathematics the easy way. Which one is easier to find? LR or MR? Which one? Somebody online tell me. Somebody type in. Somebody typed something a while ago. I didn't see it. I can't read the chat now. Somebody wrote LR. It's 2/3 OP plus 2V. Good try. You leave out the negative. Somebody said MR. No. MR is not easy to find. To use MR now, to find MR now, you have to come down here using this half of this vector that we had earlier. And then do this. You have to calculate. To use the MR, you have to calculate something. Right? To do the LR, you don't have to calculate nothing. You can look at it and see how you go from L to R. Look at it. You can come down here using minus 2u and then add this 2v out here. So additionally, if you look at the diagram, you technically know the portion vector of L, you know. It is this, OL. You know OL. I also know OR. So LR would be simply OR minus OL if you wanted to calculate. But if you're going to use MR, we did not calculate the portion vector of M. We did not calculate OM. We did not. OM will require more work. LR don't require no work. You can literally look at the diagram and see LR. You can look at the diagram and see how you go from L to R. From L to R, we're going to come minus 2u. See the 2u there? But we're going in the opposite direction to it. So that's minus 2u. And then plus 2v out here, 2v. So it's minus 2u plus 2v, you know. So LR is easier. Let's do the mathematics the easy way. LR is easier. All right? So let's write what it is here. So LR, let's just write what it is. Let's just write and then copy it down. We're going to use LR as I said. So based on this diagram, the LR is easier. It is minus 2u. To go from here, you come down minus 2u. And then you add the 2v. 2v out here. So this is what we're going to use, this one. Let's cut and paste on the next page. We're not using the MR. The MR is more work. Do the mathematics the easy way. Now, the only thing I'll say is that because this vector has the u second, I'll put another way. This vector has the v first. I'm going to rewrite this and just turn these values around and write LR instead as 2v minus 2u. 2v minus 2u. Because if you did OR minus OL for it, the OR, remember, is 2v, you know. Minus the OL, remember, is 2u, you know. So you'd have gotten it that way if you calculate it. But because we use the diagram, that's how we got this first. But calculation would have given us this way. All right? So that is now LR. So we're at the stage now, we want to show now that these two vectors are parallel. And these numbers easy to work with, you know. Remember, the aim is to bring them to a state where you can equate them. Now, initially, I would have said, just get rid of the fractions out of this one by multiplying by a 2. But these numbers easy to work with because this is a half. If you multiply this by 4 instead, it will become equal to that. So instead of multiply by 2 to get rid of the fraction and then multiply by 2 again to make it come equal, just multiply by 4 to make them equal. Everybody can understand that? Online, everybody understand that? Good. Your aim is to get the vector components to be equal. You want a side here and a side here to be equal. You realize that if you multiply this by 4, then this half will become 2 just like that. So will this half become 2 just like that. So it makes sense, instead of multiplying by 2 alone to get rid of the fractions, this time we're going to multiply by 4. Remember, the whole aim is to make the 2 vector sides become equal so that they can equate. All right, so this one is straightforward for us. We're going to multiply this one by 4 to make them become equal. So multiply this by 4 first, we got 4 LM. Then multiply this half V by 4, it becomes 2V. Multiply this half U by 4, it becomes 2U with a minus. So now they are equal, see? Now these components are equal, see? They equal the same thing. So because them equal, it means that 4M LM there equal a LR there. So you can now equate. All right? So let's equate. We can now equate the vectors. I have brought them to a state where they are equal, vector components are equal. So you can either write LR equals 4LM, or you can write 4LM equals LR. Don't matter. Let's put the larger one on the left side. So we're gonna write LR equals 4LM. LR is equal to 4LM. So I've gotten to where we want to get to, which is one vector equals a multiple of the next. And there is a common point. In this case, the common point is L. So I've underlined it. You have to write the 2 conditions for collinearity. You're trying to prove that the points are collinear. Write out the 2 things that make them collinear. First thing is that they are parallel. LR is parallel to LM. You can put the vectors on it if you want. All right? You can put on the vectors on them if you want right here. The second thing that is happening, that the L is a common point. State it. L is a common point. You can draw a conclusion and say, therefore, because of these 2 things happening, the points involved, L, M, and R. So therefore, L, M, and R are in fact collinear. That is how you prove collinearity every time. That is it. 4 marks for doing all of that. You want that 4 marks. But go to that.
Yes, sir.
But online okay? Or one person answer. But must answer, you know.
Yes,
right,
sir.
All right. All right, let's do another one. More maths equals better maths. Let's stand down, see? Let's do another one. All right, so another one was on January 2023. There's one on June 2023 as well. All right, let's do the one on 2020. I don't remember which one is one, but I want to ensure that we get the various types. So let's find the one on 2020 and see what it is. January 2020, COVID year, right here. Let's look at the vectors on that one. I want us to get the various types. All right, so this is 2020. On the back, on here somewhere. Where are you? Where are you? Not too far. All right, here's a vectors question. All right. This one kind of similar to the one that we just did. Well, let's do it still, no problem. I want us to do some of the ones with the values, right? Like the coordinates and so on. But let's do this one. Let me look at 2023 first. Let me look at 2023 first. But this one is asking us for collinearity as well. See there? So I prefer for us to do another type first. See, this one asking us for collinearity as well. Let's just check out 2023 first, January 2023. Right here. I'm looking for one that has those numbers, and those column vectors, that type. All right, let's see. This is another diagram. And I like to set the diagram ones. Let's look at 2017. If you find one on 2017. We'll come back to those if necessary, but I want to ensure that we get a variety of types done. All right, yes, we can maybe do this one. See, this one gives us some coordinates and so on. All right, let's do this one. I'm not really asking a lot of stuff, but let's do it still. At least it, it's different. All right, yeah, let's do this one. So this is 2017. Let's do this one. All right, so this one gives us some points. It says the graph below. So sometimes vectors come like this as well. All right, it's not just A and B and V and Q and V all the time. Sometimes they give us values and graph and so on. Same thing. So the graph below shows the points P, Q, and R relative to an origin O. So these are your points P, Q, and R relative to an origin O. Remember, if you know the coordinates, then you automatically know the position vector because they carry the same values. All right? Question says, we have to write as a column vector the vector OP. All right, let's write down some coordinates over here based on this diagram. We can write down the column vectors. All right, so firstly, P right here. P is a point 4, -1. Let's write it. P is a point 4, -1. So it automatically means that the vector OP is 4, -1, like that. It is not complicated. PQ, Q is this point, 0, 2. Q is a point 0, 2. So it means that the position vector of Q, OQ, is a column vector 0, 2, like that. And then R is a point 3 across, 7 up. That's what R is, 3, 7. So R is a point 3, 7. So the position vector of R, OR, note I put my R on all my position vectors, put the R on top of them. We'll have the same values, 3, 7. All right? So we're making a note of that. All right. I know they're asking us for OP, which is this one, 4, -1. So we're just going to write it that OP is 4, -1. Oh, they asked for others too. No. 4, -1. All right. And look here now, they're asking for QR. Now, because we have the diagram, we can literally see what QR is on the diagram. And we can calculate it, but we can also see what it is on the diagram. QR really is asking, how do I go from Q to R? As if we are doing a translation. How many units left or right? How many units up or down? That's what you write it. Let's look at the diagram and do it, and we're going to calculate it as well. So let's use the diagram method to go from Q to R. To go from Q to R. Let's look at it. You go horizontal first. And make sure you check the grid. Every centimeter is a unit horizontally. Every centimeter is a unit vertically. So to go from Q to R, horizontally we'll go 1, 2, 3 units to the right. That's 3 units this way. And then we will go 1, 2, 3, 4, 5 units upwards. 5 units upwards. I'm telling you that the vector QR is on this diagram is 3, 5. 3, 5. Diagram shows me that. 3 to the right and 5 up to go from Q to R. So the vector QR is 3, 5. It's like a translation from the starting point to the ending point. But the calculation can give us this 3, 5 as well. Look at it. Using the formula, displacement formula, O times the last minus O times the first. Remember, we just get 3, 5 a while ago, right? Let's remind ourselves. We got 3, 5 by the diagram. Let's see if we get 3, 5 by calculation as well. So QR by calculation would have been OR, which is O times the last, minus OQ, O times the first. O times the last minus O times the first. The OR, let's remind ourselves of what OR is. OR, remember, is 37. 37. Minus OQ was 0.2. That was on the y-axis. See here? 0.2. 0.2. 0.2. If you work this out, you're going to get 3 minus 0 is 3. 7 minus 2 is 5. So you see, you get the same answer, diagram, and calculation. All right, that is it. So you can trust an answer like this because the diagram is consistent. The diagram shows it that you got 3 to the right and 5 up. But okay with that?
Yes, sir.
All right, beautiful. All right, let's continue. The next part wants us to determine the magnitude of QR. That's just the modulus of it, the length of it. So since we have the vector QR is 3, 5, then the modulus of QR, which is written like this, is the square root of the 3 squared and the 5 squared, because it's Pythagoras' theorem. Modulus is obtained through Pythagoras' theorem. 3 squared plus 5 squared. That's 25 plus 9. That's 34, don't it? Square root of 34 units. I can leave it like that. 25 plus 9 is 34. Look at the diagram, you're seeing the same thing. The modulus is the length. Because you're actually now trying to find the length of this line. Put it in blue for you. The length of this vector QR. This is vector QR now. Going this way. And trying to find the length of it. So if we're working in this triangle here, then this side is 3 and this side is 5. Pythagoras' theorem tells you that that length becomes the square root of the 3 squared plus the 5 squared, which is the same calculation we have down here when you use a formula method. All right, so everything is consistent. But good so far?
Sir, could you repeat that, please?
Yes,
I'm
sir.
saying, what we did by calculation, we have to recognize that the magnitude is the same as the modulus, is the same as the length. It's like you're trying to find the length of the vector QR. Since QR is this vector, we know that this 3 means 3 to the right from Q, and this 5 means 5 upwards to reach R. 3 this way and 5 this way. And so this red line now is a vector QR. For to just sketch it back. This magnitude business is talking about how long is this red line? How long is it? Pythagoras' theorem in a right angle, because this is not a right angle triangle, you know. That's what it is, you know. This is now a right angle triangle, this triangle right here. It is now a right angle triangle. This side is 3, this side is 5. 5 units and 3 units. 3 units and 5 units. So Pythagoras' theorem says that the length of that red line will be equal to this. Square root of 3 squared plus 5 squared. That's what I was showing on the diagram a while ago. I'll show it on the diagram again up here. See there? This is 3, this is 5. That's how we get from Q to R. 3 to the right, 5 up. That's what this vector means. You go from Q to R, you go 3 to the right, 5 up. Why is this 3 to the right? Because it is positive. Why is this 5 up? Because it is positive. When this is positive, you go to the right. If it was negative, you go to the left. When this is positive, you go up. When this is negative, you go down. So the vector that you're seeing here is how you go from Q to R. going X and Y direction, like a displacement vector. So the column vector is like a displacement vector, like a translation in transformation. That answers the question better?
Yes, sir.
All right, good. All right. The next part now says, on the graph provided, we have to draw the vector OS and then show that PQRS is a parallelogram. All right. We must draw this vector OS. Now remember now, if the vector, position vector of S is 4, 7, then it means that S is the point, not 4, 7, 7, 4. S is the point with the same values, 7, 4, just like this. So the vector OS is 7, 4 as a column vector. Then the coordinates will have the same values. This is the position vector. These are the coordinates. They have the same value. So to locate the point S on the diagram, we're going to find this point. And then the vector now is going to be the line from O to S, O to that point. Let's locate the point on the diagram now. 7, 4. Let's go for it. 7, 4. All right, let me take these off first. We don't need these. And these. That was just for illustration. So putting on the point S, let's put it on in red so it becomes glaring. 7, 4, we said. Let's write it again. OS is 7, 4. Therefore, S is a point 7, 4. So it's 7 to the right, or to here, 4 up to here. See the 4 here? So we're talking about this point is where S is. Right here, that's where S is. S is right there. So the vector they're talking about, OS, is a straight line from O to S. You have to draw it. The question said draw it. So you can't just put it on the point S. The question said draw the vector OS. So you know you have to draw a straight line from O to S. Like this. Use your ruler and draw it. I can't draw a straight line with this device, but that is good enough. That's a vector that you're drawing with your ruler. And then I'm going to put a small little OS on it like this. And say this is the vector OS. But I understand that S is the point toward here, 7, 4. Let me shift these down. S is the point 7, 4. So S point right here is a point 7, 4, because the position vector is 7, 4. Coordinates and position vector have the same values, because both of them is how you get to the point from the origin. That is the vector OS. About to go to that. And then now they want us to show the parallelogram. Let's do the parallelogram in blue and show how you prove that you have a parallelogram. It's a popular question in C-Sec now, to prove a parallelogram or to show that a quadrilateral is a parallelogram. So I'm going to show the parallelogram now. So I'm going to join these 2 points and join these 2 points. I'm going to draw over these black lines just for emphasis. So that blue thing is my parallelogram now. That's what I said. Let me see if that was said. I don't draw the right thing. Let me see. Make sure. You say, yeah, PQRS, right? PQRS is a parallelogram. So that is that blue thing. PQRS. So that blue thing, we need to prove that it is a parallelogram. So let me show you how you prove parallelogram in vectors now. You have to show that this PQRS satisfies the properties of a parallelogram. What are the properties of a parallelogram? The opposite sides are parallel and equal in length. If you're using a vectors method, it means that the opposite sides are equal vectors, because equal vectors have the same length and are parallel. So to prove this, let me show you what we need to show. Move this over here and tell you what we need to show to prove that it's a parallelogram. So to show that that thing is a parallelogram, we need to show. Let me write it out for you. We need to show two things. You have to show that the opposite sides are equal vectors. You have to show that the opposite sides are equal vectors. And you want to use vectors maybe that you already have in this calculation so that you don't have to calculate everything. What are the vectors that we already have? We already have QR, don't it? We found QR right here. Remember? QR. So we therefore need to show that QR equal to PS. So we have to show that PS is equal to QR. Those two opposite sides are equal vectors, going the same direction. So QR is going this way. We have to show that PS is the same equal vector as QR. So that's the first thing we have to show. That PS, vector PS, we have to show that the vector PS is equal to the vector QR. So one have to work out the vector PS and show that it is equal to the same thing as PR, which it is, you know. You can see it, you know, because to go from here to here, again, you will go 3 to the right and 5 up. 3 to the right and 5 up, but I think they want a calculation method. The next thing you have to show now is the other pair on the other side. All right, so we have to show the other side, which is these two sides now. So let's say we're gonna go this way. Let's say we're gonna go P to Q and S to R. I'm sure that PQ and SR are also equal vectors. PQ, I will also show that PQ is the same as SR in vectors. The vector PQ is equal to the vector SR. The opposite sides are equal vectors in that quadrilateral. That's what makes it a parallelogram. So this is what we have to prove that that thing is a parallelogram. That the opposite sides are equal vectors. All right? That's what we need to show. Let's copy it down. So we're doing that down here. So remember, we already know QR. So we need to calculate PS. Let's do it over here in purple now. Let's do it in purple. Let's do the work in purple. What do PS first? So PS is OS minus OP. The OS is this 7,4 minus OP. What was OP again? I don't remember. OP was 4 negative 1. 4 negative 1. 4 negative 1. When you write this out, that is the PS now. When you write this out, you're going to get 7 minus 4, sorry, is 3. And 4 minus a negative 1. This minus becomes a plus. Becomes 4 plus 1 is 5. Remember, QR was 3,5 up from up here. Remember? QR is 3,5. So I've satisfied the first thing. This is equal to QR. So we'll do the first one already. Tick on the first thing. We don't need to know this now. But we don't have any of these vectors yet. So we have to calculate both of them. Let's do the PQ first. The PQ, again, is OQ minus OP. OT on the last minus OT on the first, which is equal to, what was the OQ again? It was on the y-axis 0, 2. And the OP is the same 4 negative 1. What does it work out to? This work out to negative 4. 0 minus 4 is negative 4. And this is 2 minus a negative 1. That is 2 plus 1 is 3. Okay, let's do a quick check if this calculation is right. To go from P to Q, we're saying go 4 to the left and 3 up. Let's just check it. 4 to the left and 3 up. Let's check it. To go from P to Q. Make sure it's right. To go from P to Q, the calculation is to go 4 to the left. 1, 2, 3, 4 to the left. That's it. 4 to the left, 3 up. 1, 2, 3 up. See there? 3 up. Good. Diagram and calculation match. Good to go. Just need to show the calculation on this side now, over here. Over this side. And then we're done. What is R again? R is the point 37, right? 37. Yeah, 37. All right. Let's go back down here now. We're going to do the next vector now. So this is PQ. Is this. We need to work out SR, because we didn't work it out before now. So we're going to do SR now. So SR now is OR minus OS. O time the last minus O time the first. The OR, just said it a while ago, it is 37. Just said it a while ago, you know. Yeah, 37. 37 minus the OS is this 74. 74. So you're going to do 3 minus 7. That gives us a -4. And 7 minus 4. That gives us 3. Same vector as this. So you're going to write that this is equal to PQ. So the SR is equal to PQ. And that means that the vector, the quadrilateral, it means that the quadrilateral is a parallelogram. I want to just make this like a smaller. Yeah, like that. That's it. We're done. We're proving both of them. So we can say, therefore, PQRS is a parallel. This means parallel ogram. Done. Shown. But go to that. But okay.
Yes,
All
sir.
right. So the 2 questions, right? Let's do another one. All right, let's go back to the one that we were looking at before. Let me see. June 2023. Let me see what is there. Let's go June 2023. Let's look at this one and see what happens. Let's see what kind of question is here. All right, there's a vectors question. Nice, the number of parts. Okay, let's do this one. And we can go back to a diagram one after this. So this one don't have no diagram, this is straight calculations now. All right, straight calculations. Let's crush this one now. Let's go. So this one says, it's a vectors question in section 2. Gives us these vectors, WX, XY, ZY. And it says, a vector, we have to determine a vector other than 5, -1. Remember, you know, this is 5, -1, you know. That is parallel to WX. Remember, the WX is 5, -1, you know. The WX is actually 5, -1. And they're asking us to determine a vector that is parallel to this 5, -1, but don't write 5, -1. It is any vector that is a multiple of that. So we can write 10, -2 will be parallel to that, because it is 2 times that. Let's write it like this. Let's do it this way. The vector that the one, we're going to call it V. We're going to put it as 2 times the WX, because it's a multiple of the WX. So it is going to be 2 times this, 10, -2. That's an example. It don't have to be 2. It can be any multiple you like. WX. So any vector that is parallel to WX is a multiple of WX. So that's a good enough example. But understand that I could have used 3 if I wanted. 3. And then put 15 negative 3. Multiply this by 3. But go to that, it's just a vector. It's not one vector as an answer, you know. It's a vector, a vector. So it's any vector you decide to put. If you want to be cute, you can do something like this. That vector that they want is any constant times 5 negative 1, which then becomes 5k negative k. But because them said can't equal that, you're gonna say k is a real number, but k is not equal to 1. Because if it's equal to 1, you're going to get back the same vector. You can use any constant you want if you want to be cute. Give them that. Them have to give you marks if you give them that. But let's give them a vector. Let's keep it simple. Let's not complicate. What do I put? 3 or 2? Let's put 2. 2 times double x will be parallel to double x. And that will be 10 negative 2. Let's leave that as the answer. But that's what I'm trying to say here.
Yes, sir.
Yes, sir.
All right, good. Next one, WY. So look at what we have now. This is saying, how do we go from W to Y? And we have to use these vectors that we have. Let's look at it. We want to go from W to Y. These two can take it from W to Y. Because this is taking it from W to X. And then this is taking it from X to Y. So it's easy. So we're going to say, to go from W to Y, we're going to go from W to X first. And then, remember the plus means, and then we're going to go from X to Y. So it means that we're going to be using these two vectors to go from W to Y. So the WX is 5 negative 1 down here. 5 negative 1. And then the XY is negative 3, 7. Negative 3, 7. Do the mathematics the easy way. So this works out to be 5 minus 3 is 2. Minus 1 plus 7. Same as 7 minus 1 is 6. That is the answer right there. Them easiness is 1 mark for it. It's not complicated. It's easy. Just how you go from point to point. That's what vectors is. But go to that.
Yes, sir.
Beautiful.
Yes,
Next one, the
Yes,
want is
sir.
X. Next thing the want is XZ. Now, if we want XZ, we have to use these vectors. We're gonna have to bring this one with the Z. This is the only one with the Z in it. Now look at it now. We want XZ now. XZ we want. So to go from X to Z, to be nice, since Y is connecting the X and the Z right there. The Y is connecting them enough. So it means then, to go from X to Z, we can pass through Y. We can go from X to Y first, and then go from Y to the Z. That's what the vector equation is telling us. To go from X to Z right here, we can go X to Y first. The plus means and then go from Y to Z. Problem is that they gave us ZY, but is YZ we want. No problem. We switch around the order and change these to negative. Because the negative in vectors corresponds to when you reverse the order. So from this one, we can deduce that YZ is equal to, change this 8 to negative 8, change this negative 7 to positive 7. Because we have reversed the direction. And so we can use this XY vector here, and then this YZ vector. All right, so that's what we're gonna do. So we're gonna copy all of this down now. I just want it to be on the screen when I'm doing it. All right, see it here. Let's leave it on the screen. So see it here now. To do this XZ, we're gonna pass through Y based on the information that we have. We're gonna pass through Y because the Y is connecting the Z and the X right there. So we're gonna go from X to Y and then go from Y to Z. They gave us the XY right here. So that's good. But they did not give us YZ. They instead gave us ZY. But no problem. You reverse the order of the ZY to YZ, but then you introduce the negative on this. Because the reverse direction, the inverse direction in vectors is obtained by introducing the negative. And so all we have to do now is add this vector and this vector, and we'll get the answer. So the XY is the 3, 7. From here, that's the XY, 3, 7. And the YZ is now this. Negative 8Y. Negative 8, 7, negative 8, 7. And you work this out now. Work this out. So this works out 2. 3 and negative 8 is negative 5. 7 and 7 is 14. That is the answer right there. Gotta go to that? Yes?
Sir,
Yes?
isn't it XY equal to negative 3?
Come again? It's negative 3 they
XY.
gave us? Oh yeah, my mistake. It's negative 3. All right, thanks for that. Not 3, it's negative 3. My mistake. This is negative 3. All right, beautiful. Somebody's paying attention. Negative 3 and negative 8 is negative 11. And then the 7 and 7 is 14. Beautiful. Thanks for that. Beautiful. Negative 3, 7, not 3, 7. All right, lovely. All right, any other part on this? Yep, they want the modulus of that XY now. Where's XY again? XY is this guy right here, right? They want the modulus of it. So negative 3, 7. So remember XY, don't write it the wrong way. It's negative 3, 7. And this is asking us for the modulus of it. So this modulus of XY, remember it's just like Pythagoras' theorem again. It's just the square root of the 3 squared and the 7 squared. 3 squared and 7 squared. That's what it is. That's 49 plus 9. 49 plus 9 is how much? 58. So that becomes the square root of 58. Units is a length. So you write the word units behind it. All right? Okay, remember, so this simply means, let me just put a little sketch to show what it means, this XY. It simply means to go from X to Y. X is here, Y is here. You go negative 3, means you got 3 units back. So this is 3. And then you go 7 up. 7 up this way. This is the vector XY from X to Y. That is the vector XY. This is asking us for the length of that blue line. Pythagoras' theorem in this right angle triangle. 3 and 7 are the sides. So it becomes the square root of 3 squared plus 7 squared to give you this blue hypotenuse in that triangle. Now form a vector triangle out of this. Better go to that? Huh?
Yes?
Yes,
All
sir.
right. All right, good. Question done. All right, it's now 6:11. Let me do one more diagram question, collinear points. So we can run through it quick and fast. And we'll take a break. And we're gonna come back and run through some transformation. All right. I will go to yes, sir. I think we'll go to yes, sir. I can take the break now. I don't want the one more vectors.
Break, sir.
Want the break? All right. Huh? Somebody in here said one more. All right. So who want to break can break, but somebody's asked, other people ask for one. So let's do one more. Let's do one more. All right. I want us to do the one with the parallelogram. Which one was it again? It was 2020. I looked at it earlier. Let me see which one it was. Let me see which one it is. With the vector parallelogram. Let's see if it is this one. Yeah. Let's do this one quick and fast and then we take a break. Quick and fast. Then we take a break. All right. All right. This question says, PQR is a parallelogram in which PQ is U, that's right here, and PS is V, that's right here. So they give us those. Now remember, because it's a parallelogram, these two sides, they are opposite, they are parallel and equal in length. So since this vector is V, then the similar vector up here is also V. So we automatically know that this side up here from Q to R is the same vector V. Sorry about that. It's the same vector V. Similarly, this side and this side, parallel and equal. So since this vector going up is U, then the vector going up here is also the vector U. Because it's a vector parallelogram. Opposite sides are equal vectors. It says M is on this line such that QM to MS is 1 to 2. So QM to MS is 1 to 2. So it's like QM has one part, QM has one part, MS has two parts. MS has two parts. It simply now means that QM is 1/3 of the whole thing, because the whole thing is 3 parts. So it means, for example, that QM is 1/3 of the whole thing, which is QS. And the MS is 2 parts. The MS is now 2/3, because the whole thing is 3 parts. 2/3 of the whole thing, QS. We have to know this from this information. Simple as that. That's going to help us. All right? The question now first says we have to calculate the vector QS. In other words, the vector across here that we want, down here, which don't yet have. We don't know it yet, to go from Q to S. So we have to go along these vector directions that we know. The diagram is showing us to go from Q to S. We can go out to R with the V, and then come down to S with the minus U. Why is it minus U? Because I'm going in the opposite direction to the U. So simply put, this vector is equal to V and minus U. Don't need anything more than that. It's too easy to read any other way. Better go to that. Online, better go to that.
Yes.
Yes, sir.
Good. So it is like we now know this road. We now know that vector. We can now travel along it because we now know what it is. It is V minus U. We now know it. It is V minus U. We can now travel on it. We can go along it now. If we are coming here, it is 1/3 of the V minus U. If we are coming here, it is 2/3 of the V minus U. The only thing I would say is that because the vector QS is in this direction down, I would prefer to choose my direction so that I'm going this way whenever possible. Always try to go that way. It's a lot easier because if we traverse the opposite direction, we're going to have to introduce a negative on that vector. I don't want to get into that because I tend to make mistakes sometimes. So when you can go this way, better go that way because this QS is in that same way, same direction. That's the only hint I'll tell you, or the only tip I'll tell you. All right. So next part now says we have to calculate QM. That's this, you know. QM is simply 1/3 of QS. That's what we said here. Right here. Because one of the 3 parts. So this QM that they're asking us for is simply 1/3 of the whole side QS. Of the whole vector QS. 1/3. See there? This is 1/3 of the whole thing. So doing 1/3 of QS. This is QS. So doing 1/3 of that. So then it becomes 1/3 of this part and 1/3 of that part. So then is 1/3 V minus 1/3 U. But go to that, that is QM. But okay with that? Rushing through this one kind of quickly. But okay with this one online? People in the class saying this. I'm not hearing from the people online.
Yes, sir. Yes, sir. Yes, sir.
All right, good. Then now, the next part now says we have to show that MR is this vector. So to show that MR is this vector, we really need to just calculate MR. Let's look at it. Over the we'll go from M to R on the diagram. So we just need to calculate MR and show say it equal this. All right? So look at the diagram now. MR. See here, M to R. Now you can go back this way and then come across here now. To go from M to R now. But as I said, I don't want to be going in the opposite direction to the QS. So I prefer that we go from M down to S first, and then from S up to R. Prefer that one. Where the MS is 2/3 of the whole QS. That's what I have to recognize. The MS down here is 2/3 of this whole QS. Let's write it out. We want to prove this, but we're going to calculate MR first. All right? And then show that it is equal to this. So see here now to go from M to R. We're going to go M to S. And then S to R. Let's look back at the diagram and make sure that's what we do. Yes, we'll go M to S and then S to R. Now remember now, the MS is 2/3 of QS. Let's write that. 2/3 of QS. So this MS is really 2/3 of QS. The whole thing is QS. And the SR is just a U. Let's look at it. The SR up here is just a U, the vector U. So just add in the vector U right here. So this SR is just U. I want to finish it. The QS, remember, was V minus U. We're now doing 2/3 of this. So then this becomes 2/3 of this part, which is 2/3 V, and 2/3 of this part, which is minus 2/3 U. And then you're adding back this U. So it's plus U. And remember now, you want to consolidate the values. Consolidate the values. So this is now like a whole U minus 2/3 U. Or if you like, you can write this whole U as 3/3, so that I have the same denominator as this one. We need to consolidate these U values. It's going to be 3U minus 2U, give us 1U, 1/3 U, 1U/3. So it's a 1/3 U. If you can look at it another way, it's a whole U minus 2/3 U. A whole minus 2/3 is 1/3. So this then becomes equal to 1/3 U. That's when we consolidate these U values, plus this 2/3 V. I'm going to put it here. 2/3 V. I'm doing that because they have them in that order. You have the U first and then the V second. That's why I'm doing that. So I'm going to add back the 2/3 V right here. And it is clear now that if I factorize 1/3 from these two expressions, as they have here, 1/3 out of this leaves me with the U inside here. And 1/3 out of this 2/3 leaves me with the 2. The 2V. I'm going to factor out the thirds. I'm going to the plus 2V. Which is what they had right here. So that has been shown. The last part now tells us that T is the midpoint of PQ. Prove that R, M, and T are collinear. Let's look at it now. T is being introduced as a midpoint of PQ. Let's put on the diagram. T is the midpoint of PQ. So PQ here. T is the midpoint. So I'm going to introduce the P. Let's put it in blue. Introduce the T right in the midpoint here. So I'm going to move this U. Divide that U. Let's change the color of that U. Let's shade it out. I'm going to shade out this U. I'm going to put that point as T. So this point, I'm going to put it as T, put it in blue. So this point here, we're going to put it as T. Remember, the whole thing is U, you know, and this is the midpoint. So because that is the midpoint, it divides the U half and half. So it means then from P to T is a half U. And from T to Q is the other half of U. Right here. Because the whole thing was a U and the T divides it half and half. And the points that we need to show that are collinear are T, M, and R. T, M, and R. So we need to show that these 3 points, try it in purple. These 3 points are collinear, which you can see it on the diagram. So how do we show that those 3 points are collinear? Again, it's the same thing. Parallel vectors with a common point. You need to find 2 vectors between these 3 points. We have a vector between M and R already. We just worked it out a while ago. We have the vector MR already. So naturally, we're going to use that one. So we're going to be using MR, that we just found. We have it down here. We're going to be using MR. See it here, where is it? It just works it out here, so we're going to use it in this format. So let's write it down what we're going to use. We're going to use MR first. I'm going to use MR. Let's write down what we're going to use, which is a third U plus 2/3 V, using the expanded form, so we can see the separate components. And we need another vector now. So since we use a vector connecting the R and the M, we need a vector with a T in it now. Let's look at the diagram. Which one is easier to use? So we have this already. So somebody tell me now. TM, or TR, which one is easier to find? Yes, on this diagram. Somebody online tell me. Which one is easier to find? The vector TM or the vector TR? Look at the diagram carefully. Which one is easier to find? Which vector is easier to find based on the diagram? TM or TR? Which one? We know that we're using MR already of one of the vectors to show that the points are collinear. Come on, man, somebody unmute and tell me. Which one is easier to find? T to M?
TR.
TR. Good. T to R. Because it is obvious to go from T to R. Just going to come up to Q right here, so, with half the U. And then from the Q, you're going to shut across here, so, with the V. So it's basically half U plus V. So no calculation needed. If you're going to go from T to M, you'd have to go use this half U, and then you have to use the QM. I remember the QM was this complicated thing right here that would require calculation. We don't need no calculation for the TR. So it's better to use the TR vector here now. So we're going to use the TR based on the diagram. It's just half U. See there, half U, and then a whole V out here. Take it out to R plus V. So this is what we're going to use, this vector. Let's cut it and carry it on to the next page. Do the mathematics the easy way. All right? Do the mathematics the easy way. So we're using those 2 vectors now, guys. Those 2 vectors. We now need to show that these 2 vectors parallel. So remember all them fractions about the place? That'll make it difficult to see the relationship between them. So we want to get rid of the fractions. So to get rid of the fractions out of this one, We simply need to multiply 2 by 3. That will get rid of the fractions for us if we multiply this one by 3. So let's do that. Multiply this one by 3. The lowest common multiple of the denominator is 3. Remember, when multiply by 3, multiply this side by 3 as well. So you're going to get 3mr equal. Multiply this by 3, you get u. Multiply this by 3, you get 2v plus 2v. Fraction gone out of this one. Then to get rid of fraction out of this one, this is a half. We're going to multiply by 2 to get rid of that half. That's all the fraction in there. So multiply this one by 2, the lowest common multiple of this denominator, it will get rid of the fraction. So when we multiply this side by 2, it becomes 2tr equal. Multiply this by 2, it becomes a u. Multiply this by 2, it becomes 2v. And so you see that they are already equal. This and this, they are the same. So it means that this vector is the same as that, because they equal the same thing. So because they are now equal, we can now equate. Jump to the last step of our process. Equate. And we are equating to say that this thing equals that thing. See here, 3mr is equal to 2tr. You don't have to guess it when you do it this way. You don't have to try and figure it out. It works out itself. So this now has 2 conditions in it for collinearity. You can underline a common point from now, which is r. So because one is a multiple of the next, because you're able to express one as a multiple of the next, it means that they are parallel. So we can write that mr, the first condition, put number 1, is that mr is parallel, this is a symbol for parallel, to tr. Put the vectors on them. That's the first condition for collinearity, parallel vectors. The second condition is that there must be a common point which I've underlined, and you can do that as well. R is a common point. And because you have these 2 things happening, we can draw the conclusion that the points R, M, and T are collinear. R, M, and T are collinear. This time I spell it with 2 L's, no problem. That is it. But okay? Come on, you don't get these things wrong in exam. All right. All right, it's now 6:35. We're going to take a 15 minutes break. Start work transformation at 6:45. It's now 6:30, sorry. 6:45, 15 minutes break. I think for the transformation, I might just have to just run into some questions. All right? Might have to just run into some questions for the transformation. But we'll see what it is. So let me pause a bit. Well, I can't pause. Let me just put up the timer. Let me just put up the timer. Starting back in 15 minutes. Some transformation. Transformation. Where's the timer? Gone. All right. All right, guys, we're back. I'm going to look at some transformation. All right. Gotta do a quick little recap of the transformation that you need to know about. In particular, one of the things is how do you describe a transformation? Because almost every transformation question will ask you to describe it, and a lot of the times people don't describe them properly. There's also some transformation matrices. I didn't want to get into the transformation matrices, but I think I'm going to touch on it still because we're doing transformation. All right. So there are basically 4 major types of transformation that you must know about. There's translation. We can just talk about it right now. It's one where the object moves from one location to another without turning, without changing size, without changing orientation, just a shift from one location to another. And the movement is usually broken down into the 2 primary Cartesian coordinate directions. So for example, if you have a triangle here, you can move that triangle some number of units to the right and some number of units upwards. Let's say move it 3 units to the right and you move it 4 units upwards at this point we're focusing on. And the image triangle is the same dimension, same size, everything. Then that translation can be represented t equals 3, 4. So it's kind of similar to vectors in a sense. So the triangle move, no turning, no change in size. And so if you're describing a translation, you want to state how many units left or right, which is this dimension or that coordinate, the 3 in this case, and how many units up or down. That's translation. When the object moves from one location to another without turning. And it's always represented by a column vector if you want to represent it as a matrix, a column vector. The other type of transformation is reflection. And reflection really, we can relate to reflection because we do reflections every day. We tend to look in mirrors a lot and so on. The key thing for reflection to remember is reflection in a line. Let me tell you the key thing to remember about reflection in a line. Let's say there's a mirror line M. And let's say we have a triangle here. Let's put a triangle like this. And ABC. There are 2 things happening here. If this is our mirror line, then the image distance must be equal to the object distance from the mirror line for each point. So this point B, for example, I'm going to start with B. It is this number of units to the mirror line, so the image is going to go the same number of units on the other side of the mirror line. So it's like this point will come about here, this point B. That will be able to be a B prime. This point is this number of units to the mirror line. It's going to go the same number of units to the other side. And so it may become somewhere over here. That's A. And A may become there. Then C again is this number of units to the mirror line. It's going to go the same distance on the other side of the mirror line to here. That's where C would be. And I always say, do your reflection 1 point at a time. A lot of the times, persons try to reflect the entire triangle all at once and run into problem. It is better to transform or translate or reflect 1 point at a time. Whatever transformation you're doing, a A lot of the times, it's better to do it 1 point at a time. In case of reflection, 1 point at a time. Now that 3 points are in place, we join them with straight lines. That's our image triangle. Now, the key thing I want to point out here is that the orientation is reversed. So if we look at the object, ABC is this way, anti-clockwise. But on this image of the reflection, the orientation is this way, clockwise. So we have to remember, reflection reverses orientation. Reflection in a line reverses orientation. And this is important because sometimes a reflection can look like a rotation, but rotation does not reverse orientation. A lot of the times you might get a diagram with an object and an image, and they ask you which transformation it is, and you might be thinking that it is a rotation, or you might be thinking that it's a reflection. To make the distinction, you can check the orientation. If the orientation is reversed, then you know you have a reflection in a mirror line. Because reflection in a mirror line is the only transformation that reverses orientation. What do I mean by the orientation? How the letters go around the point in alphabetical order. So A to B to C on this object is anti-clockwise, while on the image, A to B to C is clockwise. The orientation has been reversed. All right. Now, let's talk about the reflection matrices. There are some reflection matrices that is good to know. The questions, a lot of the times, are centered around your knowledge of those matrices. I'm going to see those in some of the questions shortly. There are about 4 of them, or 5 of them. Let me list them out for you, that you should know. Some of the mic is open. Mute your mic, please. Mute your mic. All right. You have to find a way to memorize these matrices if you want the exam questions to be easy. I don't want to be figuring out these things in the exam room. I use a method that I call follow the negative sign. So for reflection, the first matrix I remember is the y-axis reflection matrix. The matrix for reflecting over the y-axis. The y-axis reflection matrix. It has the first negative one in it there, right there, -1. So -1, 0, 0, 1. That is the y-axis reflection matrix. It will reflect point over the y-axis for you. How it works is, for example, if you have the point 2, 3, and you want to see where this point goes after reflected in the y-axis, you can multiply it with this matrix. -1, 0, 0, 1. And when you're using this point in your calculation, you use a column vector for it. For the point. The column vector for this point is this one. You cannot multiply with this matrix because it will not be conformable. I'm not going to get into that because we're not doing matrices. So you use a column vector for this point to reflect it. And when you multiply the matrix, this transformation matrix for reflecting over the y-axis to this point, it tells you where this point will go. The -1 times this 2 is going to take you to -2. And then this 1 times 3 is going to make this remain 3. So it means that when you reflect over the y-axis, this point will go to -2, 3. And you can literally see it because if you have a y-axis here and an x-axis, I have the point 2, 3 over here, 2, 3. If you reflect it over the x-axis, it's coming over here. So it is the x value that is now negative. The y value stays the same. So this point over here would now be -2, 3. All right, that is what would happen in this case. So this matrix will do the transformation for you. And that's how all of those reflection matrices work. So I'm going to continue listing them out. So if this is the y-axis reflection, then the x-axis reflection is easy to know. the negatives on this diagonal reverse. And so the x-axis reflection matrix is 1, 0, 0, negative 1. That's our reflecting in the x-axis. Then we have the matrix are reflecting in the line y equals x. Y equals x reflection matrix. That one is the one that looks like the identity matrix for multiplication. But the negative ones are on this diagonal over here. On this diagonal. That is the reflection matrix. The matrix for reflecting in the line y equals x. Then if you know this one, then it's easy to know the line y equals minus x matrix. So for y reflecting line y equals minus x, these ones become negative ones. Negative 1 each. So this is 0, negative 1, negative 1, 0. Those are the 4 main matrices that you must know for reflecting in lines. 4 main matrices that you must know for reflecting in lines. Y-axis, x-axis, y equals x, y equals minus x. There's also a matrix for reflecting through the origin, but I'm not going to bother with that one for now, because that is the same as a 180-degree rotation about the origin. So those are the reflection matrices. All right? That's reflection. When describing a reflection, all you need to do is state the mirror line. When describing a reflection, just state the mirror line. So that is reflection. The other kind of transformation that you should know about is rotation. A rotation has 3 components. It has a center of rotation. It has a direction of rotation. And it has an angle of rotation. Something about direction that I want to point out. Clockwise rotation is positive rotation. Anti-clockwise rotation is negative rotation. Sometimes a question will say a rotation of positive 90 degrees. I have it wrong, you know. I have it wrong. It is the anti-clockwise that is positive. I have it wrong. The anti-clockwise is positive and the clockwise is negative. My mistake. So they'll give you a positive 90-degree rotation. It is anti-clockwise 90 degrees. Let me shift it here. And if you give you a negative 90 degrees rotation, that is a clockwise 90 degrees rotation. So anti-clockwise is positive, clockwise is negative. So sometimes instead of saying clockwise, you put the negative on it. Let me write it here. This is clockwise. And this is anti-clockwise. So sometimes instead of saying anti-clockwise, you can put the positive on it. Anti-clockwise. All right? Now, there are also some rotation matrices, but they are for rotation about the origin that you must know. If you know those rotation matrices, a lot of the questions will be easier for you. When describing a rotation, you must state these 3 things. The angle, direction, and the center. A lot of times people forget to state the center of the rotation. They tend to focus on the angle and the direction. And forget about stating the center. You have to state the center when describing a rotation. It's kind of crashing through what we need to know. So what are the rotation matrices that we must know? These are rotation matrices about the origin. About the origin. Meaning the origin is the center of the rotation. The origin 0, 0. The 90 degrees anti-clockwise rotation. Remember, it is positive. That matrix about the origin, you know, that matrix has a negative 1 up here and 1 down here, 0, 0. It's good. It's a good matrix to know. Anti-clockwise 90-degree rotation matrix is this one. This matrix will show you where a point goes when you rotate it 90 degrees anti-clockwise about the origin. Then the clockwise 90 degrees one, this is anti-clockwise 90 degrees. Anti-clockwise 90 degrees about the origin. The clockwise rotation, these values switch around. So the clockwise 90 degrees, which is now negative, is a negative rotation when it is clockwise. That matrix, the negative one is now down here and the one is here. That is the anti-clockwise, that is the clockwise, sorry, 90 degrees rotation about the origin. Clockwise 90 degree rotation about the origin. Then we have the 180 degrees rotation about the origin. 180 degrees rotation about the origin. And I'm not going to say clockwise or anti-clockwise because the result of a 180 degrees clockwise rotation is the same as an anti-clockwise 180 degrees rotation. It's a full turnaround, a turnaround. So if I rotate this way 180 degrees from here to here, or I rotate this way 180 degrees, the end result is the same. So I don't need to state the direction. So it's a 180 degrees rotation about the origin. It is -1, 0, 0, -1. This matrix, it has the combination of the y-axis reflection and the x-axis reflection. And I explain that later. So this -1 is for the y-axis reflection. This -1 is for the x-axis reflection. So those are your rotation matrices that you should know about the origin. All right. The next kind of transformation is enlargement, or called size transformation and enlargement transformation. An enlargement transformation, it has a scale factor usually given the symbol K, and it also has a center of enlargement. That does not have to be the origin. So enlargement has those two components. The scale factor is the main thing that decides how the enlargement will go. The main thing is the scale factor. Let's talk about one or two other things with the scale factor. If the scale factor is a value greater than 1, like for example, if the scale factor is 2, then the object is going to be twice the size and twice the distance from the center because of the 2. So the image is twice the size, twice as large, twice the size, twice the original size, twice the size of the object. The image is twice the size of the object. In addition to being twice the size of the object, it is twice the distance from the center of the enlargement. So it's twice the size, twice as large, and twice the distance from the center. If this was a 3, then it would be 3 times the size, 3 times the distance. If this was a 4, then it would be 4 times as large, 4 times the distance. Another thing is that because the scale factor is a positive, the image and the object will be pointing in the same direction, and they'll be on the same side of the center of the enlargement. I'm going to do some examples and show you. But here we're going to remember the image and the object, they will point in the same direction. I'm going to do some examples and explain all of this just now. You watch by the video and repeat this. That's when the scale factor is positive, because we have a positive k. When the scale factor is positive, that's what happens. All right? Let's say the k is a fraction now. If the k is a fraction, like for example, a half, then the image is going to be smaller than the object by a half. So in this case, the image is smaller by a half. Image is half the object. In size. But also it is half the distance from the center. So you're going to say, and half the distance from the center of the enlargement. We'll get a couple of enlargement questions to do. And again, if it is positive, then the image and the object will be pointing in the same direction. Let's look at when the scale factor is negative now. Like for example, a negative 2. For example, this is a simple number. When scale factor is negative 2, it's going to be twice as large again because of the 2. And twice the distance from the center. But the negative will cause it to be inverted on the opposite side of the center and pointing in the opposite direction. So when the scale factor is negative, the image and object, they will point in opposite directions. And there'll also be an opposite side of a center. The center is between them. Center between them. Center will be between them. I'm just trying to abbreviate what will happen. Center will be between them. But the 2 will still make it twice as large and so on. If the scale factor, for example, again, was negative half, then we put the word larger up here. So it's going to be larger. The image is larger. That's right. Image is larger because of the 2. But the negative now caused this. So in this case, if it's a half, then the image is smaller by a half. Image is smaller. And then now the same thing here happened for the negative. The same thing that is happening up here because of the negative, the same thing is happening up here. Well, I'll do some example. I'm just trying not to spend too much time on this part of it so we can get to the question. Because if I were to go through and explain everything from scratch, believe me, we're not going to finish because transformation is a vast topic. All right? I want to get to the questions. And if you describe an enlargement, naturally, you have to give the scale factor and the center. You have to give both things, scale factor and the center. There's one more thing about enlargement I want to talk about, which is enlargement area. A lot of people mess up enlargement area. I'm just going to state it now and I'm going to put down a couple of examples. The area of the image of an enlargement is the scale factor squared times the area of the object of the enlargement. You have to remember this. The area of the image of an enlargement is the scale factor squared times the area of the object of the enlargement. A lot of people believe it's a straight k times, but it's a scale factor squared. I'm not going to bother to explain it why now, but that is what it is. We're at the stage now where you have to just know some stuff. Students in my class should already know why this is so. All right, just kind of crashing through some of the important things. Compound transformation. If you have 2 transformations and the 2 of them are 2 by 2 transformations, 2 by 2 transformations. If you have 2 by 2 transformations, I mean by the 2 by 2 matrices. I mean not the translation not involved, because the translation is a 2 by 1 matrix. The 2 by 1 translation, 2 by 2 transformations. And they are, for example, L followed by M. If you have 2 transformations, 2 of them are 2 by 2. One is L and one is M. And do the L1 followed by the M1. Then the single transformation that is equivalent to this. So this is going to be equivalent to a single transformation. Given by M times L. Second one times the first one. So we like to say something like this. So it's like to say something like this. L followed by M is ML. Second one times the first one. L followed by M is M times L. So you multiply the 2 of them to get a single matrix. We're going to do an example with that. All right. There are a couple other things. Like for example, 2 reflections over intersecting lines is equivalent to a rotation. Give you an example. If you do a reflection over the y-axis and do a reflection over the x-axis, let's use the white line y equals x. Y equals x. Let's do this example quick. So if I have the y-axis and x-axis, and if I have a point P, and I reflect P over the y-axis to here, and then I reflect it over the x-axis, over the line y equals x, sorry, to here, and it comes here. Then to go from this original spot to this final spot, and put in x-axis, x-axis. Then it is equivalent to a rotation. So if I reflect over this line, let me take out the x-axis. So we'll leave the 2 lines that we use it. If I reflect over this y-axis and I reflect over this y equals x, then the single transformation that goes from this to this is a rotation. So from this to this is a rotation. So 2 reflections over 2 lines, 2 mirror lines that intersect. Those 2 blue lines, for example, they intersect at the origin O right here. The angle between these 2 blue lines is 45 degrees. The angle between the y-axis and the line y equals x is 45 degrees. You're going to get a rotation that is 2 times that angle. So this rotation is going to be 90 degrees. So these 2 reflections that we did from here to here and then from here to here is equivalent to 1 rotation. The rotation angle is twice the angle between those 2 mirror lines. Angle between the y-axis and the y equals x is 45 degrees. So the rotation angle is twice that, 90 degrees. And the center of the rotation is the point where the 2 mirror lines meet. That is the center of the rotation, where the 2 mirror lines meet. If I had 2 reflections over 2 lines that are 90 degrees apart, like for example, the y-axis and then the x-axis. And again, I have a point P here. I'm going to reflect it over the y-axis first to here. And then I reflect this over the x-axis. So this distance goes down to about this distance to here. So I did 2 reflections over 2 lines that are 90 degrees apart. The y-axis and x-axis are 90 degrees apart. And this is my final position out here, P prime. but I came a reflection here and then a reflection here. That's two reflections over two lines that intersect. That is equivalent to, again, a rotation. So from here to here is a rotation over to here. And the center of rotation is this origin. So this rotation is going to be 180 degrees. Why? Because the angle between these two mirror lines is 90 degrees. So two reflections over intersecting lines is equivalent to one rotation. The rotation angle is twice the angle between the two lines, and the center of the rotation is at the point of intersection of the two lines. The y-axis and the x-axis intersect at the origin. So this would be the center of the rotation, the origin in this case. These are key things that will help you to know the answer to some questions. Two reflections over lines that intersect equivalent to a rotation. The angle of the rotation is twice the angle between the mirror lines, and the center of the rotation is the intersection of the mirror lines. And the set questions that test your knowledge of this. Last thing I'm going to tell you about is two reflections over parallel lines. So two reflections over parallel lines is equivalent to a translation. So if I have a triangle, for example, like this, I reflect over this mirror line first, it's going to go like this. If I reflect it over this one again, it's going to come back like this. So you see, what we did a translation from this one over to this one. This one went to a translation to get that one. So two reflections over parallel lines is equivalent to one translation. From this to this would be a translation. And the translation distance is twice the distance between the mirror lines. So the distance between mirror lines was, for example, 5 units. And the translation from here to here would be 10 units to the right. These are some things that are good to know for some of the questions. All right. I think I'm going to just jump to some questions now after that. Oh, one more thing. Remember the enlargement matrix, we didn't write it down, above enlargement about the origin is K00K. We spoke about enlargement matrix, enlargement about the origin. The enlargement matrix E is K00K. That's when the center is the origin. When the center is the origin. And this matrix, it maps a point, put a different color. It maps a point XY onto KX, KY. That's what this matrix does. Maps a point XY onto KX, KY. All right? And remember, it's only when the center of the enlargement is the origin, we can use that matrix. The K is the scale factor. So scale factor is 2, for example. I have a point, say 3, 5. I apply a scale factor of 2 to this point, K equals 2. And the center is the origin O, then it's going to go to 610. Because the scale factor of 2 is going to double the coordinates to 610. All right? That's a quick recap, guys. I mean, I can't go through all of this properly. I'm kind of rushing through because I just want to get to some questions. All right? So the first one I'm going to do is on 2015 because I want to show the enlargement thing that I just spoke about. So let's go to 2015. Where are you? This is actually June 2015. Right here. And transformation is a topic that can appear. You can get 2 transformation questions on the exam paper. You can get 1 in section 1, 1 in section 2. There's always 1 in section 1 with the diagrams and so on. All right. Let's look at this one, 6B. I just wanted to use this one to show the enlargement thing. 6b. Where is it? 6b. Did I pick up the right paper? All right, there you go. Let's do this one. So this is a transformation question. This is the object. This is the image. All right. This question says the diagram below shows triangle PQR and its image P prime, Q prime, R prime after an enlargement center C. So this is the center of the enlargement. Let me tell you something that can pick up right away. Firstly, the scale factor is negative. K is negative. Why is the scale factor negative? Because the image and the object, they are pointing in opposite direction. Look at it. If you look at the line, for example, RP is pointing up on the image, upwards. But RP on the object is pointing downwards. So the scale factor is negative because the image is inverted. The scale factor, negative scale factor inverts the image. In addition to that, the center of the enlargement is between them. When the center of the enlargement is between the image and the object, the scale factor is negative. The next thing, what is the value of the scale factor? The value of the scale factor is 2. All I know is 2. This side QR is 2 units, but this image side is 4 units. So it's a doubling of the size. So the scale factor is actually -2. I know that before I even do anything. The negative is because they are pointing in opposite direction. The 2 is because the size is doubled. The image is doubled. In addition to the image being doubled, the distance from the center is also doubled. Look at it. From this center point to R is 1 unit. From the same center point to R prime is 2 units. But it is in the opposite direction. Opposite direction because it's 2. So this was 1 unit from the center. It is now 2. The image is now 2 units. So the distance from the center is also doubled. You can look at yet another point. Take the center up to P, for example. That distance. It is doubled up to P prime. This length is twice this length. This length up here to the image is twice this length. So the distance from the center is also doubled. But it is in the opposite direction. That's why it's a negative. So when the scale factor is negative, the image and the object will point in opposite direction. When I do an example, they are pointing in the same direction afterwards. So these are some of the things to pick up right away from this question. The scale factor is negative. And the value of it is 2 because the size is actually doubled. All right? That's what I wanted to point out to everybody. Everybody understand that online?
Yes, sir.
All right.
Yes, sir.
Good. Let's answer the question now. Question says, use information from the diagram to complete the statements below. The size of the scale factor. Size means that you don't put a sign on it. You know. The size of the scale factor is 2. Is 2. The size of the scale factor is 2. The scale factor is actually -2, you know. This is a scale factor, you know, -2, you know. But the size of it is 2. This says now the scale factor is negative because, why is it negative? Why is the scale factor negative? Because the image and the object. Huh? Somebody said something? Somebody was answering that question. Why is it negative? Let me hear. Oh, all right. Nobody's saying anything. So why is the scale factor negative? Negative because, I would say because the image is inverted. See, it is inverted because this was pointing down and it is now pointing up. Like another side. R to Q was pointing this way. R to Q is now pointing this way on the image. It is inverted. The image is inverted and it's on the opposite side of the center. See, R is over here, R prime is over here, and R is over here. So the image is inverted on the opposite side of the center and pointing in the opposite direction. That is why the scale factor is negative. Let's write it out. The scale factor is negative because the image is inverted, turn upside down. It is inverted on the opposite side of the center. The image and the object are on opposite side of the center, and the image is also, and it is also pointing in the opposite direction. As the object. It's pointing in the opposite direction that the object is pointing in. That's why the scale factor is negative. They give you a nice number of lines to write out the reason. They give you a nice number of lines to write out why is the scale factor negative. That's what they want to say. This is a key statement to make. That it is inverted on the opposite side of the center. So maybe if you just write this alone, they'll give you the marks, you know, inverted on the opposite side of the center. Maybe if you write that alone, they'll give you the marks. But I like to add this to it as well, that they are also pointing in the opposite direction. The image and the object are pointing in opposite direction. That's what happens when the scale factor is negative. Watch this now. If this was the object and this was the image, and the transformation was this way instead, then all that would have meant that the scale factor would have been a negative half. Negative half would be the scale factor if this was the object and this was the image, and the transformation was the other way. If it had gotten smaller, if it was big like this first and gotten smaller, the scale factor would be a half, but it would have been negative still. But understand that? Good. Let's continue. Down here it says, the length of PQ is root 13. The length of PQ is root 13. What is the length of P prime, Q prime? P prime, Q prime is the image, you know. The scale factor of 2 is going to act on this, you know. So the length of it is going to be twice the original length. The image is twice as large. The sides on the image are twice as large because of the 2. The negative is just a direction thing, but the physical size is twice. So this is going to be 2 times square root of 13. 2 times. Because of scale factor of 2, the value of the scale factor is 2. 2 times the square root of 13 units. But understand this? But understand that?
Yes.
Online, everybody understand that? Good.
Yes, sir.
Good. Next one now. See this one now, testing the knowledge of area. See? The area of triangle PQR is, we need to calculate the area of triangle PQR. They want it. Let's go on the diagram and see it. The area of triangle PQR, that is the original triangle, you know. What is it? So this question is testing our knowledge of area now. It's just half base times height. See that? So this base is 2, this height is 3. So it's half 2 times 3, which becomes 3 units square, because the half and the 2 cancel. Everybody say that? Can leave this calculation up here so if you want to know.
Yes, sir.
Show it, you know. So it's half 2 times 3 is the area of this triangle, which works out to be 3 units square, right? So let's put a 3 on this. It's 3 units squared. 3 units squared. If you want, you can show the calculation under here and say it is half 2 times 3. That's why it is 3 square units. You have the object triangle, the original triangle. Watch this now. This question is testing your knowledge of this that I told you earlier. Area of the image of an enlargement is k squared times the area of the object of the enlargement. This question is testing your knowledge of that. Did you know? The area of the prime triangle is something times. What is that something times? K squared. The scale factor squared. The scale factor is -2. -2 squared. If you want, you could put 4 there instead. Well, let's write it. It is -2 squared because the scale factor is -2. Now, whether it's positive or negative, when you square it, it's going to come out positive anyway. And this -2 squared is 4. So the area of the image triangle is 4 times, because it is the scale factor squared times the area of triangle PQR, which is 4 times 3. This is supposed to be 12 squared units. Area of the image is 12 squared units. A lot of people go and put it as 6 because they say the scale factor is 2. They think the area is double. No. The relationship is a squared relationship, as we have here. And we can check if this 12 squared is correct. This 12 unit squared is correct. Look at the image triangle, the area of the image up here. This 12, see here, this image. This side is 1, 2, 3, 4 units. This side up here is 6. 1, 2, 3, 4, 5, 6 units. Up here, so it's 6. The area of this triangle is half 4 the base times the height of 6. See, that works out to half of 24, which is 12 units squared. But they don't want it to work it out this way. They want it to apply this knowledge down here. So they write the question to test your knowledge of this. Yes? Huh? Farzan. Touch him now. The driver come. Sleeping Tom. Alright, everybody good with that? Everybody okay with this question? Everybody good with
Yes,
that
sir.
one? Alright, beautiful. Alright, let's do a more recent questions now. A more recent question now. Let's look at 2021. There are 2 questions on 2021 that are transformation. 3C and 10B. Yes, transformation is a topic that you can get 2 questions on one exam paper. Transformation. Because they usually give the matrices 1 in section 2, and they give a normal construction 1 with graph and so on in section 1. So we're looking at 2021. Where are you, 2021? 2021, right here. All right. This is paper that we just did earlier. And I'm saying there's a transformation question on this. Number 10. See it here, 10B. I don't really want to do that. That's too basic. I don't really want to do that. Let's go down to number 3C. There you go. This is another enlargement question. So can we do some other types afterwards? This is another enlargement question right here. Let's do this one. All right. This question says the letter A and the point C66 over here, see there, C66, are shown on the grid. So they give us this A and this point 66. All right, pay attention now, guys. It says on the diagram, draw accurately each of the following transformations. An enlargement of the letter A with a scale factor of 2 about the point 66. So from this point 66, they want us to do an enlargement of this letter A of scale factor 2. So the scale factor of 2, we know that this A, it has to be doubled in size. But in addition to being doubled in size, you have to double the distance from here. So for example, this point, the distance is going to be doubled. Colin, your driver is here. Right? The distance is going to be doubled. So we have to construct that triangle by knowing that the distance from the center to this point A, all of these points, is going to be doubled. All right? And we have to construct it. So how do we do that? How do we do that doubling of the size? Let's focus on this point here first. This distance right across this diagonal here is going to be doubled. Right across these two diagonals, it's going to be doubled. So this point on the A is going to come out across another diagonal to here. That's where this point is coming. It's coming to here. Because this distance is doubled out to there. But can you understand that? What about this one? This distance must also be doubled. Right? You can use a ruler and measure the length of this and double it. But look how you can do it quickly now. Watch this now. We can double this distance by using these coordinates. Use these coordinates to double this distance. Watch this. This length broken down into coordinates is this number of units down. 1, 2, 3, 4 units down and 1 across. So to get the same distance again from here, we can do another 4 units down, 1 across. Look. 1, 2, 3, 4, 1 across. So this point is coming out to here. See there, so it's coming out to here. This point is coming out to there. So that's where it is supposed to be. Hold on a second. Hello? Yes, yeah, man, it's out. It just went out. All right. So this point is coming down to here. So we already know 2 points on the A now that we're gonna get to now. This is the point that was here before, and this point is now down here on the enlarged A. Now we don't have to construct anything more now. It said this time between these 2 points here and here on the A, it's also gonna double. So this 2 units between the, let's call it the foot of the A, it's going to double to 4 units. So this is the end of this foot. So the end of the other foot is going to be 4 across here. 1, 2, 3, 4. 1, 2, 3, 4. So it's coming to here. And you can literally construct it. See there? If I draw a straight line through here and double that distance, it's coming down to there. So those 3 blue marks represent where the A will form. You can literally join them now. See here, join this one. Join this one. That's my image A. That's the start of it. I need to put in this cross line right here now. So if you look at it, this cross line, look at it. Let me take out these red lines. This cross line in the middle there is going to double. It is about 1 unit from the top or from the apex up here. So it's not going to go 2 below it. But look at it, it's not going to exactly come on this line, you know. It's a little bit above it. So still it has to go above, right? So it's going to come down to about here. This is where it's going to be, that cross line. 2 units down. It was about 1 unit down here. That distance is going to double. Everything is doubled. So that is where that cross line approximately will be. So that is my image A right there of the enlargement. But I appreciate that.
Yes, sir.
That is it. All right. So what we did, we used the fact that the distance from the center is doubled when the scale factor is positive. And because the scale factor is a positive K, if you notice, the A pointing up and the A on the image also pointing up. If the scale factor was a -2, then the image would have to be over on this side of the A, of the C, of the center point. All right? But that is not the case this time. That is the image A. Hope everybody understands that. Next part wants us to do a translation on that A. -3, 2. So all that is going to happen is that we're going to take this A, I want to move it 3 units to the left. That's what this negative means, 3 units to the left. If it was a +3, it would mean 3 units to the right. And this 2 is how many units vertically will go. Because it is positive, we're going to go up. So like we're going to take the A, we're going to move it 3 units to the left, this way, and 2 units up. 2 units up. So moving all points on the A by this translation. Because this is negative, that's why we go this way. If it was positive, we would have gone that way. 3 units to the left and 2 units up. That's why we're moving this A. Let's put a different color for that. Let's do it in red. So let's start with this point here. 3 units to the left and 2 units up. 1, 2, 3 units to the left, 2 units up. 1, 2. So this point is coming to right there. Right there. Let's put it in purple. The new one. Right there is coming. Now technically we don't have to do anything else, you know. We can literally now just make back the same size A around this point, knowing that this point corresponds to that. So look at it. From this leg is 1 across, 2 down. And because of translation, we can do the same thing. 1 across, 2 down to where the foot of that leg is going to be right here. Same thing on the other end. 1 across, 2 down takes me from this apex to this foot of this leg. So see there, 1 across, 2 down to here. So those 3 spots are where the main points on my A is gonna be. So I just need to join them with straight lines now. So I do the translation on 1 point, and then I draw the same shape around that 1 point. And then I need to put in this diagonal thing across there. Notice it is a little bit above the halfway mark. Do the same thing, a little bit above the halfway mark. Give the examiner that and you get your marks. You just need to draw it with a ruler. I just can't draw it straight on this device, but that is it. But go with that.
Yes, sir.
Nice and easy, beautiful. That finishes that question. Let's go back out to the number 10B still, because it's still a transformation question. Let's go back out to it. 10B. Right here. Look, a simple question. Look what it says. It says triangle M has these vertices, X, Y, and Z. Those are the vertices on triangle M. It says when M is transformed, that's triangle M, you know, is transformed with the matrix, this matrix, the image is M prime. Now you have to know this matrix. This matrix is a reflection in the line Y equals X. The more things you know, the better. This matrix reverses coordinates. So if you have a point, for example, AB, it reverses the coordinates to BA. Because the same line we reflect in what we're doing inverse matrix, inverse function, reflecting line y equals x, and the coordinates are switched around. If you don't know this, you can actually test a calculation. Apply this matrix to a test point. So 0, 1, 1, 0, multiply it with this test point. We have to use the column vector format of it and work it out. You will get 0 times A is 0, and 1 times the B is B. So this value up here is a B. They're gonna get 0 times, you're gonna get 1 times the A, which is A, and 0 times the B is B. So the second value is A. So you can see that the values switch around. This calculation is confirming that AB is mapped by this matrix 0, 1, 1, 0 to the point BA. BA. So the image of these points is also obtained by switching around the coordinates. And that's what they wanted us to do. Coordinates of the image. So all you have to do is switch around these. You can leave this on the paper now for the examiner to see how you get the answer. Just switch them around. So x prime, if you switch around 1, 1 is going to remain 1, 1. Why is that? Because 1, 1 is on the line y equals x. And it is called an invariant point. An invariant point is a point that does not move. It does not change under a transformation. So because the point 1, 1 is on the mirror line, when you reflect a point that's on a mirror line, in the same mirror line, it stays where it is. Then this point, which is 3, 1, its image y prime is going to switch around to 1, 3. And then this point z, which is 3, 4, the image point z prime, the value is going to switch around to 4, 3. That's what this transformation matrix does, because it's a matrix for reflecting in the line y equals x. These questions become easy when you know these things. That's why I say you need to know those transformation matrices, because the questions will always be centered around those. Those are the ones that they're going to give you on the questions for the most part. So this one finished. That is it. 2 marks for that. All right? So you don't want to waste a lot of time for these 2 marks. And all you need to do is know what transformation that is. So that finishes that question. All right, so we have done 2 so far. 2 down. Let's see how many we can do, because transformation is such a vast topic. We want to do a number of them. What time is it now? All right, we have over an hour to go. All right, let's do one on 2020. 2020 apparently has 2 questions as well. Let's look at 2020. Let's look at the 2020 paper. January 2020. Over there. See it here? Let's see what question is on this one. All right, so we'll just do a question on this. So we have all those markings. And here's a transformation question up here. Beautiful. Number 10E right here. All right, let's do this one on a diagram. This question says, transformation, this transformation, 0p q0. It transforms the point R to R prime as shown in the diagram. Transform R to R prime. That's what this transformation matrix does. Let's look at it. It transforms this R up to this R prime. Looks like a rotation. Don't know. Cannot assume. Looks like an anti-clockwise 90-degree rotation about the origin. So if that is the case, it will be 0, -1, 1, 0. If it's an anti-clockwise 90-degree rotation about this origin. Let's see what it is. Let's work it out. We can calculate it because we know the coordinates. We know the points. All right? So the question says, what are we supposed to do? Determine the value of P and Q. So what we're going to do, we're going to use the fact that the matrix 0P Q0, when you apply it to the point R, let me shift this down. Let me show it up here. What is that matrix? I call it M? Yeah, I call it M. Let's write it this way now. When you apply the matrix M to the point R, the image is R prime. That's what you're basically saying. When you apply matrix M to the point R, the image is R prime. Question, what are these coordinates? R and R prime. Let's go for them. So R is the point here, which is 2, -5, 2, -5. And R prime up here is 5 across, 2 up, 5, 2. It is 5, 2. All right, so those are the points we're going to use in the calculation. Let's copy it and paste it down here. All right, and we are saying this transformation matrix, when it's applied to R, the answer is R prime. So we're setting up an equality of matrices. All right, so what we're going to do is, okay, we'll multiply by the matrix for R, for this one, which is 2, -5. It gives us the matrix for R prime, this one, which is 5, 2. All right. So what it means, guys, is that this row times this column is equal to that 5. How do you multiply this row by this column? It is the first element in the row times the first element in the column, second element in the row by the second element in the column. That will be equal to this 5. So let's write that as an equation here in purple. So the 0 times 2 is 0. And the p times -5 is -5p. That is equal to the 5 right here. So this then, if you divide by the -5, you see that the p is actually equal to -1. Then for the q now, it is this row times this column that is equal to this 2. How you do it? This first element in the row by this first element in the column, this second element in the row by this second element in the column, those products add up to 2. So we can set it up. So it's a q times 2, which is 2q. And the 0 times -5, which is 0. That is equal to this 2 over here. So in that case, the q is equal to 1. Okay, divide by this 2, the q is equal to 1. So the matrix is as I suspected. The matrix is actually that same matrix that we said. The matrix, the P is -1, right? See there, the P is -1 right there. So it's 0, -1, and the Q is 1, 1, 0. And they are now asking us to describe it. The best way to be able to describe it and get the 2 marks, 3 marks to describe it, is to know the matrix, rather than have to go and figure it out. This is the anti-clockwise 90-degree rotation about the origin. That's why I say it makes sense to know those matrices that I wrote on the board earlier. So I'm going to describe it now. This matrix M is an anti-clockwise -90-degree rotation about the origin. That's what that matrix is. An anti-clockwise 90-degree rotation about the origin. And because we are describing a rotation, you have to make sure that you state the 3 components. You state the name of the transformation is rotation. Rotation has 3 components. It has an angle, which is the 90 degrees. We stated that. It has a direction, which is the anti-clockwise. And it has a center, which is the origin. You make sure that all 3 are stated in your description. You have to ensure. A lot of people would forget to write the origin, about the origin, and lose a mark. Don't let that happen to you. All right? Also, instead of saying anti-clockwise 90 degrees, we could have said positive 90 degrees. Remember, anti-clockwise rotation is positive rotation. But that is it. Anti-clockwise rotation is positive rotation. But go with that. Anything else? I think this question done. But okay with that? All right. There's another question on this same paper. 3C. So you see, you can get 2 transformation questions on the paper, guys. So transformation is a topic that you absolutely must know. Here's another enlargement. But this time the scale factor is positive. You have to leave? All right, no problem. All right, this time the scale factor is positive. I can look at it and know some stuff from now. The image and the object, they are pointing in the same direction. Look at it. PS pointing this way on the object. PS pointing the same way on the image. So I know that my K is a positive value. What is that value? It is 3. Because, for example, this side PQ is 1 unit, but P prime Q prime is now 3 units. So it has gone from 1 to 3. So the scale factor is a positive 3. So the scale factor is 3. We know that already. The next thing we need to find is the center of the enlargement. I'm sure we're going to need the center of the enlargement. Question is, how do you find the center of the enlargement? The center of the enlargement is found by joining corresponding points and extending them back until they intersect. That's what you do to find the center of the enlargement. So for example, I can join P and P prime. So the center we know is on this line connecting P and P prime. This line. P and P prime are on the same horizontal line. So the center is somewhere on this line. Then I can join Q and Q prime. I don't have a rule line, but I can get it. Q and Q prime. And they extend it back. So it's looking like it is this point right here is the center. Put it in blue. Where those 2 lines meet is the center of the enlargement. We can check it. Because if the scale factor is 3, then the distance of the image from that is also going to be tripled. So we can check it. Let's say the distance to P. So the distance to P here is just 2 units. 2 units to P. So P right here, sir. No, this is P. From the center to P, if this is the center, the distance to P is 2 units. If this is the center and the scale factor is 3, which you know it is 3, then that distance is going to be tripled. 2 units, another 2 units, another 2 units. Yes. This is now 6 units. That's tripled from 2 to 6. P has tripled out to P prime in distance from this point right here. So this, in fact, is the center of the enlargement. Everybody understand that? Students understand that? Online, you understand that? I got this point and I just double check it if it also triples the distance from the center. The distance of P was 2 units. Since the scale factor is 3, it's going to move this point to 6 units away from the center instead of 2. Triples the distance from the center because the scale factor is 3. I want to know the scale factor is 3 because I just look at this side was 1 unit. It has tripled to 3 units up here. So the scale factor is 3. It's a positive 3 because the image and the object pointing in the same direction. It is not inverted. And if you notice, both of them are on the right of the center this time. Both of them, the image and the object, are on the same side of the center. That's another way you know that the scale factor is positive. But I can agree with that online. About good? Online?
Yes, sir.
All right. So now we're going to answer these questions now. So I basically went ahead of myself because I know they must ask for the description. They must ask for the description. Right? And if we're going to locate, this is -1, -2, -3, this is -4, 1. So this point is -4, 1 right here. -4, 1. This center point, the center of enlargement is -4, 1 right here. They're going to ask us to describe it. Must ask you to describe it. All right? So might as well just get it from now. All right, let's go now. Question says, write down the mathematical name for the quadrilateral PQR. That's a trapezium. See it? It has one pair of parallel sides. Same here. One pair of parallel sides. A trapezium. Easy question, this one. Trapezium. Trapezium. Next part says, PQRS is mapped onto P prime, Q prime, R prime by an enlargement. They're telling you of scale factor K about a center point AB. Use the diagram to determine the A, B, and K. We know them. The K is equal to 3. And the center point CAB, we worked it out, it is C negative 4, 1. That's what we got here. So this is the point C that I'm talking about. This is the point C. That is the point negative 4, 1. So it means then that the K is 3, because that is the scale factor. The A is negative 4 and the B is 1. So let's write that. The A is negative 4 and the B is 1. That's what they asked us for, the values A, B, and K. But good at that? But okay? Online, everybody okay with that?
Yes, sir.
Yes, sir.
All right, cool. Next question. Oh, that one finished. I want to know if the visitors are okay now. You're my regular students answering. What about the visitors, the person who are not normal in the class? Are you okay? Like, for example, Marquita. See Marquita here. Are you okay? I don't hear anything from Marquita. Malachi. Malachi, is that Malachi? Malachi, you good?
So how do you get the K to equal to 3 again?
Because I look at how the size changed. Let's look at it again. I looked at how the size changed. So for example, this side PQ was just 1 unit before. And the image distance, the corresponding image now is 3 units. To go from 1 to 3, you have to multiply by 3 to get that. So the scale factor is 3. See that? You just take
Yes,
any
sir.
one side and compare it. Take any one side and compare it. That's what we did. All right? Any one side. If you look at this side down here, look at this side, another side. This side PS was 2 units. It is now 6 units. See there, 1, 2, 3, 4, 5, 6. So it has gone from being 2 units long to 6 units long. How you do that? You multiply by 3 to do that distance, to do that that extension or that length change. So the scale factor is 3. All right. Anybody else have a question? Anybody else? Don't be shy. All right. Tamaya Thompson, you good?
Yes, sir.
All right. What is this? Tariq? All right. Don't be shy. If you don't understand something, just say it. All right. All right, let us do another one. Let us do another one. That was 2020. Let's look at 2018. Let's look at 2018. Wrong paper, wrong paper. All right, 2018, number 6. If I'm going to pass it already. Yeah, I'm going to pass it. Number 6. There you go. All right, so this question is a nice question. Remember this one. This one is going to test your knowledge of compound transformation. So I said the diagram below shows triangle PQR. This is triangle PQR. And they're going to want us to do a couple of things. First, they want us to do state the coordinates of the point R. So R is right here. This is 2 on the y-axis and this is 4. So here the y value must be 3 and the x value is 0 because it's on the y-axis. So R is a point 0, 3. Nice and easy. So R is the point, 0 is the x value, 3 is the y value. Next part says, draw on the diagram. On the diagram below, we have to draw these things. P prime, Q prime, R prime, a reflection of PQR in the line y equals 1. So we want to reflect this, triangle in the line y equals 1 to get this triangle. Now the line y equals 1, you must know, is a horizontal line passing through 1. Let's draw that line y equals 1 and then reflect. So y equals 1. So 1 right here, so this is the line y equals 1. Horizontal line here is y equals 1. I want to reflect this triangle in this line. Image distance equals object distance. Do it 1 point at a time. Let's zoom it up. So this point P is 1 unit to the mirror line. It's going to go 1 unit on the other side to here. So it's coming to here. I'm going to put P prime there. Then R. R is 2 units to the mirror line. It's going to go 2 units on the other side to here. That's where the R is going. That's R prime. R prime. And then the Q. The Q is 1, 2, 3, 4 units to the mirror line. It's going to go 1, 1, 2, 3, 4 units on the other side of the mirror line. Coming down to here. It's coming down to here. This length is 3. This is going to stay 3. But Q prime is now here. So now that I have the 3 points in place, then I draw the triangle. Don't try to reflect the entire triangle all at once. You use a rule and draw these things. I don't have this app not allowing me to draw straight lines. All right. So I'm just going to draw it with my friend like that. That's the prime triangle, the first one. The next part, so we have done this. The next part says we have to draw a double prime triangle, a reflection of the prime triangle in the line x equals 0. The key here now is to know that the line x equals 0 is actually just the y-axis. The y-axis is the line x equals 0. Remember, if it was the line y equals 0, that would have been the x-axis. You have to know these things. So instead of just saying y-axis, they tend to sometimes to give the equation of the line. So the y-axis is the line, the x-axis is the line y equals 0, and the y-axis is the line x equals 0. I'm just writing this for information. Oh, they want us to reflect in this. In fact, let me take this off, kind of relevant to the question. So I want to reflect now the second triangle, this one, in this y-axis to get the third triangle. So let's go. So this line that I'm reflecting in next is the y-axis. So let me draw that here. So I'm going to be reflecting this line, which is the line x equals 0, which is the y-axis. So I need to reflect this triangle now in that line. Now, firstly, this point is on the mirror line. Let's put that one in purple, the third one. This point is on the mirror line. This point, R, it's on the mirror line. So it's going to stay there when you reflect it in that mirror line. It's going to stay where it is, right here. So R prime and R double prime is the same point. right here. It's called an invariant point. This point Q is 2 units to the mirror line. It's going to go 2 units on the other side to here. So here is where Q double prime is going to be. And then P prime is 2 units to the mirror line up here. It's going to go 2 units on the other side to here. So that is where the P double prime would be. Remember also that this point is still R prime, R double prime. All right, maybe we'll put it here. R double prime is the same point. They want to join those with straight lines. So join this one, join this one. Let's move this R out the way. I want to join this one. Let's put about R prime in blue. Let's put it right here, R prime. And that is it. Now, let us think about what we did. Because the next question is going to relate to what we just did. What we did a reflection in the line, y equals 1. Let's use a different color. Let's use this brown. That color, let's use that. Right. So we did a reflection in the line, y equals 1, followed by a reflection in the line, x equals 0. So we did 2 reflections over 2 lines that intersect. So to go from this to this is a rotation, because 2 reflections over intersecting lines is equivalent to a rotation. The rotation angle is 180 degrees. Why? Because the angle between the 2 mirror lines here is 90. This horizontal line and this vertical line, angle between them is 90. And because they meet right there, the center of this rotation is the same point where they meet, right here. That becomes the center of the rotation, 180 degree rotation. That point is 0, 1. 0 is the x value, 1 is the y value. This point is the point 0, 1. 0, 1. So we have a rotation about the point 0, 1. And that rotation is clockwise. Why is it clockwise? Because we came here first and then we went across there. So it is clockwise. If we follow the order of the process that we did. Let me take this out. So we must recognize that the single transformation from this one to this one is a 180 degree clockwise rotation about this point where those 2 mirror lines meet. How we know that? Because 2 reflections over lines that intersect is equivalent to 1 rotation. The rotation angle is always twice the angle between the 2 intersecting mirror lines, and the center of the rotation is the point of intersection of the 2 mirror lines. All right, not going to say that anymore. Let's see what the next question is. Look what it says here. It says, describe fully the single transformation, that maps the double prime triangle back onto the original triangle. So we know that to go from the original triangle to this one is a 180 degrees clockwise rotation. About the point 0, 1 and 0. But they're asking us to do the transformation for the other way. They want us to do the rotation of the transformation from this one to this one. So therefore we have to reverse it. We have to give the inverse of it. It's the purple one they want to know. But we know the blue one. Because the blue one is what happened. But it's the purple one they want. So the purple one is just the inverse of this one. And the inverse of a rotation is just a rotation in the opposite direction, same angle, same center. If you look at the diagram, to go from this one back up to this one, we just need to rotate the other way. Sorry, to go from this back up to this, which is what they want, we just need to rotate back the other way, anti-clockwise 90 degrees, about the same center. So you see, if you don't know that two reflections over intersecting lines is equivalent to a rotation, you can't get that question right. I have a problem getting it right. The more things you know, the better. But this question is also testing your knowledge of an inverse rotation, because I want the opposite direction to what we got. We were expecting them to ask us what this transformation is. But they ask us the other way. They ask us what is this transformation. It is the inverse of this one. And so we're giving them the answer for the purple one. The blue one is what we got, but they want the purple one. So the purple one is a 180 degrees. Sit here, describe it fully. It's a 180 degrees. It's going to be anti-clockwise. Rotation about the point where the two lines meet, which was 0, 1. That is it. Opposite direction. Make sure we describe it properly. We gave the name rotation. I must have 3 components: angle, direction, and center. The center is not origin this time. It is this point, 0, 1. But understand that one? But understand that? Before we move on, everybody understand that one?
Yes, sir.
All right.
No, sir.
You don't understand it? Somebody said no. Somebody said no. Did somebody say no? All right, I'm not hearing anything. All right, let's move on. The next question now says that triangle PQR undergoes an enlargement of scale factor 2. So this is a K equals 2 enlargement. It says we have to just calculate the area of the image. That's all I want us to do. So this question is testing our knowledge of this. Area of image is K squared times the area of the object. That's what this question is testing. Area of image is K squared times the area of the object. So what is the area of the object? We have to look at the triangle. This is the object, triangle PQR. We need to calculate it up here. Look at the diagram. What is the area of this triangle right here? That's our object. Let's work it out over here. Area of the object triangle. This side is 3. You can treat this as a base and treat this as a perpendicular height 2. All right? So it becomes half 3 times height of 2. This becomes 3 units squared. That is the area of the object, 3 units squared. That's the area of this triangle. Treat this as the base, treat this as a height. 3 by 2. So we're going to come down here now and apply that. The area of our object is 3 units squared. That's what we just worked out a while ago. 3 units squared. And the scale factor is 2. That's what they told us. So the area of the image that they want, the area of the image becomes 2 squared, scale factor squared, times the area of the object, which is 3. That becomes 12 units square, because this is 4 times 3 is 12. This question is testing your knowledge of this. You know, you have a profile on exam paper about knowledge. This is an example of knowledge. It will affect your profile if you can know that. That's why you get the area of the image. K squared times the area of the object. You must know these things. All right. That's number 6. I don't think there's another question on this for transformation. The last one. I think there's no more transformation on this one. Let's see. This is matrices. I'm gonna do a marathon on this next week. Matrices, right? All right. So that finishes that question. That's 2018. All right, let's look at which one was this? January, right? All right, let's look at 2021. 2021. July 2021. July 2021. Right there. Question 3B. Supposed to be a question 3B there. Let's find it. Not too far. Yep. Gone too far, Mr. Shaw. There you go. Here's a transformation question right here. Let's do this one. 2021. All right. So this question says, diagram below, it shows 3 triangles, X, Y, and Z on the square base. So this is X, this is Y, this is Z. Chances are, this is your object triangle. And then you have a transformation to this one, and you have another transformation to that one. All right? Let's look. Triangle X, see there? Triangle X is mapped onto triangle Y by a reflection. State the equation of the mirror line. The triangle X go onto triangle Y by a reflection, and I want the equation of the mirror line. So this one to this is a reflection. The mirror line is halfway between them. So it's clearly, this line is halfway between them. This is 2 units to this side, for example, 2 units to that side. Obvious, right? This line is the x-axis. We have to be careful. The standard didn't ask us for which line it is in. It asked us for the equation of the mirror line. So the reflection took place in the x-axis. But you cannot put x-axis as the answer because it asks for the equation of the mirror line. The mirror line is the x-axis, but x-axis is not an equation. The equation of the x-axis is y equals 0. That is the x-axis. This is the equation of the x-axis. Y equals 0. So you cannot say your answer is x-axis. X-axis is not an equation. The equation of the mirror line is y equals 0. So you have to put this as the answer. You cannot say it's the x-axis, even though it is obvious that it's the x-axis. This is not an equation of a line. The equation of the x-axis is y equals 0. All right, enough of that. Next part says, describe fully the transformation which maps the same triangle X onto triangle Z. X to Z. They want us to describe it now. X to Z. So now we want to look at how we go from this one to this one. All right. So clearly, there is some turning. Because this side of it that was horizontal, I'm pointing out, is now vertical and pointing up. So it means that it turn by 90 degrees anti-clockwise. But you can see that? Good. So we know that anti-clockwise 90 degrees rotation now. Because what was horizontal is now vertical. The next thing we know is we need to find out is the center of the rotation. Now, most times these questions, the center of the rotation is the origin. Let's just check that. So let's say that this is the center of the origin. Let's test a couple points. This point, for example, is this unit from the center, from the origin. This is the origin. It's rotated down to here. So this point is rotated down to here. You can see it. Let's test another point. Let's say this point out here. Let's use the coordinates of it. So this is the origin, is the center of the rotation. It is coordinates, we're going to rotate the coordinates. It's 6 units across and 2 units up, that L thing. So imagine that you take the coordinates out to this point, this L looking thing, and you rotate it 90 degrees up here. So it means that this piece here is going to come now 6 units up on the y-axis. And this thing at the top of it is now vertical, is now going to go horizontal at the top of it. So you see, it takes this point over onto this point for real. So it is true that this is the center of the rotation. You only need to show it with 2 points, and you're good. So that is the center of the rotation. If you wanted, you could use distance straight. So for example, this distance out here, or the line from here to here, is rotated, and it's now up there. So this is rotated like that. And you can actually see it as 90 degrees even on this sketch that I did with my hand. All right? So you can see it. So the center of the rotation is the origin. So it's an anti-clockwise 90-degree rotation about the origin. Let's write it. An anti-clockwise 90-degree rotation about the origin. So this is an anti-clockwise 90-degree rotation about the origin. An anti-clockwise 90-degree rotation about the origin. That's what it is. The last part of this question now says, well, actually 2 more parts. It says, on the same diagram, we must translate triangle Y minus 7, 1 and label that image V. So it's minus 7, 1 means we're going to go 7 units to the left and 1 unit up. That's the minus 7, 1 translation matrix. I'm going to take a point 7 units to the left and 1 unit up. That's what this will do. And we're doing it on triangle Y, right? Right? Triangle Y. 7 units to the left, 1 unit up. Let's go. Where's triangle Y? That's this one. We're going to translate this triangle 7 units to the left, 1 unit up. Let's throw it in red. So let's say we're using this point to start. So we can just translate this point, and then draw about the same shape around this point after we move it. So 7 units to the left. So if it's at 0 and going 7 units to the left, it's going to come all the way out to negative 7 here. And then going to go 1 unit up to here. See there? Negative 7, 1 up. See there? Negative 7. 7 units to the left and 1 unit up. So this point is coming to here. Let's put that point in blue. Then after we get that point, we just need to draw back this same shape around this point. So this side of it, for example, is how many units? 1, 2, 3, 4, 5, 6. So we just need to draw a line, 6 units here. 1, 2, 3, 4, 5, 6. So this now represents this top part here. Then look at this part. This part down here is what? Can read like this. 2 down, 2 back to go from here to here. 2 down, 2 back. So it's here 2 down, 2 back to here. So this point corresponds to that. So let's take these out. Right? So this point is now here. This point is now here. And then once you have that point, you can now draw the triangle. This is that blue triangle. I'm going to take out these red markings. Don't need them. But this is now the triangle. They must label it V. That's the triangle V. The next one. Next one says we are to, on the same diagram, we are to enlarge triangle X, center O, with a scale factor of 1/2. Now this one is easy. But the center has the origin. When the center has the origin, a point XY will map onto KX, KY. The scale factor is K and the center is the origin. So all we have to do then is multiply the coordinates by 1/2. Half the coordinates to get rid of the image of this one, because scale factor is 1/2. Half the coordinates on triangle X. That's all we have to do. So we're going to go on triangle X and half the coordinates. So this is triangle X, we're going to half the coordinates, because we're enlarging from the origin. All right, still call an enlargement, even though the image is going to be smaller. Still call an enlargement. So this point is that 2 is going to half to 1. So this point is going to come to here. This point, what is it? 4, 4. It's going to half to 2, 2, which is here. 2, 2. So this point is coming to there. Then this point, it is what? 6, 2. It's going to half to 3, 1 to here. Half 3, 1 to there. So this becomes your image after the enlargement of scale factor 1/2. That is it. All right, and if you like, you can show those construction lines. So this is the center of the enlargement. So like you have this one, you have this one out here, and you have this one out here. All of those points are enlarged from there. We don't need to leave those red marks on it. Let's show them just for illustration purposes. That's the center of the enlargement. But that is it. But I'm supposed to label this one W. What did they say? W? W. Yeah, W. Label this one W. This one is W. That is your diagram. Nice and easy. Want to go to that? Online?
Yes, sir.
All right. It's now 8:25 minutes to go. Can do one more. I think this paper one another. This is what? This paper might have another one. Let's look at our number 10 if there's another one. Let's see. Let's see if there's another one, number 10 on this paper. Sometimes they have 2 transformations on them. Yep. That's why transformation is such a big topic. You need to know transformation, because it is possible for you to get 2 questions on the same paper. 2 transformations. All right, look like there's none on this one. All right. So you have gotten away. Okay. Let's find another one. We did 2020, right? We did 2021, right? Remind me. Yeah, I think we did it 2020. All right, let's look at June 2018. Let's look at June 2018. We did January 2018. Let's look at June 2018 now. June 2018. Then we'll finish off with this one. Call it a night. Next week we'll do some more work. More maths equals better maths. All right, look at some other topics next week. Down here, not too far. Let's see if there's anything early up. Here's a transformation. This one. Let's do this one. And let me see the one at the last one only. Number 10. It's more interesting. Let's see. Let's see. All right, let's do this one. It's a calculation. Yeah. Let's do this one. All right, let's do this one. All right, I think the one on number 3 is similar to what we have done so far. So let's do this one. This one says transformation T is defined by this matrix, a transformation. So this is not one of our regular transformation matrices. This is almost like a matrices question, really, right? But they bring it under transformation. It says the point 8, negative 2, 3 is mapped onto A prime AB under T. And I want us to find the value for A and B. So what it is that they're going to apply this transformation matrix to this point, and the answer is going to be this point. Let's set it up. So it's like when you apply that transformation T to the point A, you get the point A prime. So it is 2 minus 1, 2, 0, times the point A, which is negative 2, 3. That's going to be equal to the image point, which is here, AB. And so to get the AB, we just need to complete this calculation, this multiplication. So this is multiplying matrices. I mean, that's it, to multiply those matrices. So when you multiply these matrices, we're going to get a column matrix with 2 values to match off with the AB over here. So whatever value we get here is the A, whatever value we get here is the B. When you multiply a 2 by 2 matrix on a column matrix, you get back a column matrix. All right, let's go. So this red line across here is to remind me that I'm using these 2 rows with this 1 column to get the values in here. All right. So how we know which row to use and which column? This first value that we want, it is situated in the first row and the 1 column. So to get it, we're going to multiply this first row with this 1 column. How do we multiply a row by a column? We multiply the first element in the row by the first element in the column, and then the second element in the row by the second element in the column. Some teachers say you multiply along the row and down the column, same thing. What we like to say is first element times first element, second element times second element. Remember, we're using this row and this column now. So it's first element times first element, second element times second element, and then you add the values. First element times first element, second element times second element. 2 times negative 2 and negative 1 times 3. 2 times negative 2, negative 1 times 3. The 2 times negative 2 is negative 4, and the negative 1 times 3 is negative 3. So this is actually negative 7, so you know that the A is negative 7. Then this value here now, it is positioned in the second row and the 1 column. So to get it, we're going to multiply this second row with this 1 column. Multiply them the same way again. First element in the row by the first element in the column. Second element in the row by the second element in the column. First element times first element. Second element times second element. First element times first element. Second element times second element. 2 times negative 2 and 0 times 3. 2 times negative 2, 0 times 3. 2 times negative 2 is negative 4. 0 times 3 is 0. And then you can clearly see from this that this works out to -7, which is the A. So I can write it here, that the A becomes -7, because this is -7. This becomes -4, which is the B. And so I can write it here, that the B is -4. So those are the values for A and B. That's what I was asked to find. The value for A and the value for B. But understand that? Online, everybody good?
Yes, sir.
All right. Next part now says, we have to determine a matrix that will map A prime to A. What is now? This is testing our knowledge of inverse matrix. So remember now, look at it. The matrix, the point A was mapped onto A prime by this matrix T. See, it mapped A to A prime. Matrix T did that. This question is asking us for the matrix that will map A prime to A, which is a reversal of the mapping. So now we want to go from A prime back to A, this way. It is the inverse of T that will do that for you. So this question is really asking us to calculate the inverse of T. The inverse of T will reverse the mapping. It will reverse what T did. So we really want to calculate T to the -1. Let's write out what T is again. T over here is the matrix. What is it again? It is 2, -1, 2, 0. 2, -1, 2, 0. And this question is asking us to calculate T to the -1, the inverse. So the inverse of a matrix is 1 over the determinant of that matrix multiplied by the adjoint of that matrix. All right? That's what it is. That's what we calculated. Let's put it up here. That's what we're calculating. Make this smaller. We'll just have it here so we can remember what it is. It's T. We're trying to do this calculation now. So then it becomes 1 over. Now, what is the determinant of T? The determinant of T is the product of the elements on that first diagonal. Some teachers call it leading diagonal or main diagonal or first diagonal. Anything we mean first. The product of elements on that first diagonal is 2 times 0 is 0. Minus the product on the elements on that second diagonal, or they call it the following diagonal or trailing diagonal or secondary diagonal. Anything that means second. That product is 2 times -1 is -2. So that is subtracting -2. Then this minus makes this a plus. So we really have a +2 under here. So under here is really a +2. This actually becomes a +2. I'm just writing it there to remind us. Then we have to multiply that now by the adjoint matrix. How do we construct this adjoint matrix of T? Easy. You interchange the elements on this first diagonal. You switch them around. Just switch them around. That's all. So the 2, 0 becomes 0, 2. 0, 2. And then the elements on the second diagonal, you leave them where they are, but you change the sign. So this -1, for example, is going to come back in the same position as a +1. And this +2 is going to come back in the same position as a -2. And that's how you construct the adjoint matrix. You interchange the elements on the first diagonal, interchange these two first. That's what we did here, interchange them. And then we leave these two where they are, but then we change the sign of them. Leave them where they are and change the sign. That's how we get the adjoint matrix. And so the final answer now, which is the T to the -1 that we want, right? T to the -1 matrix, the inverse of T, is equal to, dividing each of these values by this +2. So 0 divided by 2 is 0. 1 divided by 2 is 1/2, or you can put 0.5. And -2 divided by this 2 is -1. And then 2 divided by this 2 2 divided by this 2 becomes a positive 1. So this right here is the answer. Let's shift it away a little bit. This is the answer right here. That is the answer. The inverse matrix will reverse the mapping. But go with that one before we move on. But okay?
Yes.
All right. And then what next? Down here now, I think we're going to finish with this question for the day. All right. This question says another transformation is given by this. It's another transformation. What do we have? We have T already, right? Remember, we have T. We have this T. Let's copy it again. And they're telling us now of another transformation. Let's paste it here. This question is not even a transformation, it's more a matrices multiplication question. But they apply a transformation to it. It said, so these are two 2 by 2 transformations. T and P, both of them. Question says, find a single 2 by 2 matrix that represents a combined transformation T followed by P. You have to know that T followed by P is PT. The second one times the first one. T followed by P is PT. So we need to calculate that product, P times T, for the single transformation. Let's work it out. P times T you have to do. You cannot switch them around. If you reverse the order, you're going to get the wrong answer because matrices multiplication is non-commutative. You cannot switch around the order. If you switch around the order, the answer could be wrong. All right? So we're calculating P times T. So we put the P1 in front of the T1. The second transformation times the first one. That's where you get a single matrix. So putting the P in front, 0, 1, 1, negative 2, multiplied by the T1 afterwards, which is 2 minus 1, 2, 0. And so we just multiply these two matrices now. It feels like a matrices question now. So this is going to work out to a big 2 by 2 matrix with 4 values. Remember, we take the rows of the first matrix. I put a line across here to remind us that we take the rows. I take the columns of the second matrix. I put a line down to remind us that we take the column. So this first element that we want here, it is positioned in the first row and the first column. So to get it, we have to multiply this first row by this first column. Multiply them the same way again. First element times first element, second element times second element. First element times first element, second element times second element. 0 times 2 and 1 times 2. The 0 times 2 is 0 and 1 times 2 is 2. That's the first value. Then this value over here now that we want, it is positioned in the first row and the second column. So to get it, we have to multiply this first row by this second column. Same thing again. First element times first element, second element times second element. First element times first element, second element times second element. So it's first element times first element, second element times second element. 0 times negative 1 and 1 times 0. The 0 times negative 1 is 0 and 1 times 0 is also 0. So this value is just going to work out to be 0. Then this third value down here, it is positioned in the second row and one column, the first column, second row, first column. So to get it, we multiply this second row by this first column. Same thing again, first element times first element, second element times second element. First element times first element, second element times second element. First element times first element, second element times second element. 1 times 2 and negative 2 times 2. 1 times 2 is 2. Negative 2 times 2 is negative 4. Then the last value out here, it is positioned in the second row and the second column. So to get it, we have to multiply this second row by this second column. First element times first element. Second element times second element. First element times first element. Second element times second element. 1 times -1, -2 times 0. The 1 times -1 is -1. The -2 times 0 is 0. So you're adding 0 here. Let's shift this box over, this bracket over a little bit. So the final answer down here is equal to, this becomes 2. This is 0 as we said. This becomes -2. And this becomes -1. That's a matrix PT. That's a compound matrix PT. T followed by P is P times T. Then down here now, it is saying, hence, find the image of this point under the combined matrix. So you're going to apply this matrix now to this point. We're going to have to multiply again. So we're applying the matrix 2, 0, -2, -1 to the column vector for this point, which is 1, 4. And you're going to multiply them again. Again, we're going to get 2 values. Taking the rows of the first matrix and the 1 column for this first value. So it is first element times first element again, second element times second element. And so it is 2 times 1 and 0 times 4. The 2 times 1 is 2 and the 0 times 4 is 0. Then this value down here now, second row, 1 column. So it is this second row with this 1 column. First element times first element, second element times second element. First element times first element, second element times second element. -1 times 1, -2 times 1, I mean, -2 times 1, and -1 times 4. So the -2 times 1 is -2, and the -1 times 4 is -4. So this then works out finally to be, this is 2, and this is -6. But the question asks for the image of a point, so you can't leave this as the answer. The image of that point, or the point corresponding to this vector, is 2, -6. So this is the image that I wanted. The image of a point is a point. You cannot give them back a vector. This is a vector for this point. And so that is the answer right there. This is the answer right there. Okay, guys, I'm going to end it there for today. And we'll do some more work next week. But you guys in here, you know you have class tomorrow. Right? Good. But online good? Everybody okay?
Yes, sir.
Everybody good?
Yes, sir.
All
Yes,
right.
sir.
All right. So next week we're gonna do some more work. I think gonna be started the same schedule. We're gonna do some classes Saturday and some classes Sunday again next week. The week after that we're gonna have a 12-hour from 9 a.m. to 9 p.m. We're gonna be working on 2 exam papers that day. So the students are gonna do it first, and then I'm gonna do it afterwards. That is the plan. All right. And then the day before exam, that's a Saturday. The day before exam is gonna be a freelance day. The person can come and just ask questions. Just bring questions that you want, anything you want clarified. Just bringing them on the last day, the day before the exam. After the paper 2, we're gonna do some marathons with paper 1. I'm gonna bin some paper 1. All right. I have a lot of paper 1 questions. We're just gonna work them out and show the similarity between the paper 1 questions and if they should repeat questions, you have to look out for the minor changes. All right. So we're gonna have some sessions after the paper 2 for that purpose. All right. So persons can aim to get 60 out of 60 on the paper one when time comes. All right, guys. So that is the plan. So you can all check in when we continue this thing. Bye, everybody. Good luck going forward. All right.
Okay.
All right. Cool. All right. Bye bye. Bye bye.